Good evening to Ananda. Good evening. Right. So till yesterday, we have discussed about this definition so-called H, that is inertia constant H, which we said as a ratio between kinetic energy stored at a synchronous speed by rating of the machine. Right. So now we are going to take up some more mathematical relations here. Yeah. First of all, if you copy this H definition, what I have taken earlier, kinetic energy stored in the rotor at synchronous speed by this rating. Generally, I'm going to take up that rating of the machine with a letter G here. I'm going to take up the rating of the machine with a letter G. Sometimes the people will use a letter of S also. G or you can say yes sometimes. Okay? Yeah. So from this, what is the kinetic energy stored in the rotor at synchronous speed? G H. So G into H also one of the formula we can say. Right. Kinetic energy stored in the rotor at synchronous speed. Only at synchronous speed we are talking. That is G into H. G is a rating of machine in terms of MVA, you can say, and H is a inertia constant in terms of megajoule by MVA. Fine. Next thing. Some other words we are going to discuss now. See, actually, kinetic energy stored formula, it is half J omega square, right? Half J omega square, omega mechanical. I am rewriting this like half J omega into omega s at synchronous speed. Okay, half J omega s into omega s. What do you mean by this J into omega s? M. So this you can write it as half m omega s at synchronous speed. Kinetic energy stored at synchronous speed is half J omega s square. Else you can write half J omega s into omega s. J omega s you can replace with m. So you can get as half m omega s. And this value you can make it equals to G into H, which is nothing but kinetic energy stored at synchronous speed. Okay? Yeah. So let's say here itself in other way. Kindly observe here. So I can write GH equals to half m omega s. Half m omega s. And what's the formula for m you can write now? What's the formula for m we can write now? That is nothing but 2 into GH by omega s. 2 into GH by omega s. So it is one of the very famous formula. Very famous formula for the calculation of angular momentum. 2 into GH by omega s. The way how you are going to substitute omega s. Kindly listen all of you. Anywhere while you are doing problems, if you get a doubt that what m value we have to use, what m formula I have to use, means you better always use this one. M is equals to 2 into GH by omega s you can use. Okay. According to the way how we are going to substitute this omega s, units will change for m. Okay. Let us say first one. I'm writing here first one. M is equals to 2 into GH by, I will keep that omega s in the form of electrical. Electrical in the sense, you can keep 2 pi f and 2 will be cancelled out and you will get this like GH by pi f. You are going to get this like GH by pi f. And what will be the units of this one? Megajoule second by electrical radians. Megajoule second by electrical radian. GH by omega s. Sorry, GH by pi f. Megajoule second by electrical radian. This is one of the units for m. Other way of writing m. Look here. Other way of writing m. GH by, in place of that pi what we have, you keep 180 degree. So if you keep 180 here, then it will be coming in terms of megajoule second by electrical degrees. Megajoule seconds by electrical degrees. All of you getting this one? How we have written m? Right? Can you write it in mechanical form? Tell me please. Can you write it in mechanical form? M is equals to, check here, 2 into GH by omega s. 2 2 into GH by omega S. Omega S means omega S mechanical. Omega S means now omega S mechanical. What is that now? 2 pi n by 60. Maybe you can write 2 pi ns by 60 also. 2 pi ns by 60. And you manipulate this if you want. If you want, you can manipulate this. Else, you write this simply in terms of megajoule second by mechanical radians. Megajoule seconds by mechanical radians. For example, if you want to get it in mechanical degree, simply you replace this pi with 180. Pi you replace with 180, you get that in megajoule second by mechanical degrees. Same m you can write as 2gh by 2 into 180 ns by 60, and this will come in the form of megajoule second by mechanical degrees. Mechanical degrees. I think all of you getting this one? The way of writing m. Clear? Maybe earlier class, in the previous class, while we are discussing about swing equation and all, we mentioned that m will be like Pa by d square delta by dt square. Accelerating power by d square delta by dt square, where we said the units will be megawatt second square by electrical radians. Same thing we have written here. Megajoule second by electrical radian in one form, other form electrical degree, mechanical radian, mechanical degree. Okay, let me rewrite the swing equation a little bit. So I'm rewriting the swing equation. Very simple thing. Don't complicate this study what I'm making. md square delta by dt square is equals to accelerating power, which is PS minus PE. PS minus PE in their respective units. Okay, now listen here. See, PS is in megawatt, PE also in megawatt. PS megawatt, PE also in megawatt. I want to convert these numbers into into per unit form. If you want to convert this PS and PE into per unit form, with what base we have to divide this one? Tell me please. S base, right? We have to divide that with S base. Not rating. Rating of machine is okay, Gopi Raju. But strictly speaking, you should say S base. That's the best one to answer. Okay. See, to maintain same balance on both sides of the equation, I will write this one like, you write the statement better. You may get a doubt again. It's like, divide with S base on both sides. Divide with the value of S base on both sides. S base on both sides. So you can get here m by S base into d square delta by dt square is equals to PS by S base minus PE by S base. I think all of you comfortable to write this one. M by S base into d square delta by dt square equals to PS by S base minus PE by S base. Okay. Now look all of you. Look, listen. Stop writing and just listen to this. Just listen. See, if you look at the units of m, megajoule second by electrical radian, else megawatt second square by electrical radians. Megawatt second square by electrical radians. For example, a simple question I am asking you, you have to convert that m value given into per unit form. We have to convert that m value given into per unit form. See, in a simple view, converting a given absolute value into per unit form means simply cancelling its units. Cancelling its units is nothing but converting a given number from absolute to per unit form. All of you getting my words? Are you clear about this one? Please tell me. Converting a given absolute number into per unit form means simply we should cancel the units of that. Okay. What are the units of m? We have megawatt second square by electrical radians. But one thing, you can't convert this time, seconds, into per unit form. You can't convert the seconds into per unit form. You can't convert the radians also into per unit form. Angle can't be converted into per unit form. Seconds can't be converted into per unit form, but megawatt you can convert into per unit form. Megawatt you can convert into per unit form. See, if you want to convert the megawatt into per unit form, with what base we should divide this m? With what base we should divide this m? Tell me please. With what base we should divide that m? Yes, base again. So in my view, m value in the per unit domain, m value in the per unit domain is nothing but m actual by s base, but still it will have their own units. But still it will have their own units, like second square by electrical radian it will be having. Okay, even though I say per unit, but still it's having some units which we can't convert into per unit strictly. Which we can't convert into per unit strictly. Okay, yeah. So I'll write here m by s base is going to be called as m per unit, but it will have some units like second square by electrical radians. Second square by electrical radians. Okay. Next, let's continue. See, this m by s base, I can keep m per unit, d square delta by dt square, ps by s base, ps per unit minus pe by s base, pe per unit we can write. So m per unit into d square delta by dt square equals to mechanical power input per unit form minus electrical power per unit form. This m per unit will have its own units like second square by electrical radian. D square delta by dt square will have some units like electrical radian by second square, and both will be cancelled out. And the left hand side is in complete per unit form, right hand side is already in the per unit domain. Okay, so I think all of you getting this expression what we have written, right? Angle and time we can't convert into per unit domain. Angle and time we can't convert into per unit domain. Okay, see, for example, if S base value, what we are saying now, itself is rating of the machine. If S base value is equals to rating of the machine, then what we can say? If S base value itself is rating of machine, what is M formula? M formula, GH by pi f na? GH by pi f by G. GG will be cancelled out. It will come to be H by pi f. H by pi f. Then M per unit is nothing but H by pi f. Even though I say it is in per unit, but still it's having some units which we can't convert into per unit domain. M per unit equals to H by pi f, second square by electrical radian. So if you want to write in electrical degree, you can keep it 180 f second square by electrical degrees. Second square by electrical degrees we can say. Correct, Sai Jaran. What's the doubt you have then? Well, base value will have same units of absolute. Correct. But still, you can't convert some what we call units into per unit form. So called seconds and electrical radian, I am saying you. Yeah. Fine. Let's move ahead. Look at this one. Look at this H actually. H. It is kinetic energy stored in the rotor at synchronous speed by rating of machine. Kinetic energy stored in the synchronous speed will be having which units? Megawatt second. Rating of machine is in MVA. Kindly observe. Again, I'm asking you the same question. Kinetic energy is stored in the rotor megawatt second, which you can convert into per unit form. Can we convert that megawatt into per unit form? Can we convert megawatt into per unit form? Yeah, tell me please. Yes, we can convert megawatt into per unit form. With what we have to divide it to convert that into per unit form? S base. We have to divide that with the S base. Can we convert the seconds into per unit form? Can we convert seconds into per unit form? No, we can't convert seconds into per unit form. So can you tell me now, what is its kinetic energy by rating of machine? What is it kinetic energy by rating of machine? Any other name you can give for it? Kinetic energy is stored in the rotor by rating of machine. What are the other name we can give for this? Name. Per unit kinetic energy. per unit kinetic energy, we can call that one. Following all of you. So the other name for the H, what we have written just now, H is also going to be called as per unit kinetic energy. Kinetic energy stored in the rotor. Per unit kinetic energy stored in the rotor. But still it is having its own units, that is in terms of seconds. It will have its own units like seconds. Clear? Done. So we'll be doing some problems in a sequence on this concept of H, M and all, right? So let's take the first one. Okay, before moving to the problems, let me recall that machines swinging together, not swinging together concept. Okay, first I'll take machines swinging together. Machines swinging together. Swinging together. Yeah. So whenever machines are swinging together, we said that the acceleration power required per unit acceleration of the equivalent machine. Accelerating power required per unit acceleration of that equivalent machine should be equals to summation of accelerating powers required per unit accelerations of all the units what you are considering. That's what we said finally. Equivalent angular momentum is summation of angular momentums of number of units connected in parallel to the same bus bar. Number of generating units connected to the same bus bar. Yeah. Let's write that M equivalent here. M equivalent. Let me go in the electrical domain. Let me go in the electrical domain only. M equivalent is G equivalent H equivalent by pi F. Clear? G equivalent H equivalent by pi F. What is M1? G1 H1 by pi F. What is M2? G2 H2 by pi F. Plus and so on. What is Mn? Gn Hn by pi F. Clear? Gn Hn by pi F. So I'm showing 160F. Please kindly complete 160F. Okay. See, after cancelling this pi F, what we can write here is G equivalent H equivalent value. G equivalent H equivalent value, nothing but G1 H1 plus G2 H2 plus and so on Gn Hn. G1 H1 plus G2 H2 plus and so on up to Gn Hn. Right? So the kinetic energy of that equivalent single unit, kinetic energy of that equivalent single unit will be equals to summation of kinetic energies. Summation of kinetic energies of all the units which are swinging together. Of all the units which are swinging together. This is one conclusion what you have to make on your own. So what is H equivalent of that single unit available means? H equivalent is nothing but summation of all kinetic energies we have. Summation of all kinetic energies, what we have here, by G equivalent value. Now, if ratings of all the machines are equal, ratings of all the machines are equal, and that is equals to G equivalent. If that's the case, you can call H equivalent equals to H1 plus H2 plus and so on up to Hn. If G1, G2 and so on up to Gn values are equal, and if that is equals to G equivalent value, then you can say that H equivalent is nothing but H1 plus H2 plus Hn. Next, similarly, we will take up machines not swinging together also. Similar manner, taking up a case like machines not swinging together. Not swinging together. Okay. Machines not swinging together means you can call 1 by M equivalent value is nothing but 1 by m1 plus 1 by m2 plus and so on up to 1 by mn. 1 by m1 plus 1 by m2 plus and so on up to 1 by mn we have. Mn. Next. Similarly, you write m equivalent, g equivalent, h equivalent by pi f, m1, g1, h1 by pi. Like that, if you do, pi f will be cancelled. After cancelling that pi f, you can write 1 by g equivalent, h equivalent value is equals to 1 by g1, h1 plus 1 by g2, h2 plus and so on up to 1 by gn, hn. Like this, you can say 1 by g1, h1 plus 1 by g2, h2 plus and so on up to 1 by gn, hn. Next thing. And if you say again, if that g1, g2 and so on up to gn values are equal, and if that is equals to the value of g equivalent, then the g1, g2 and g equivalent will be cancelled out, and we'll get 1 by h equivalent value will be equals to 1 by h1 plus 1 by h2 plus and so on up to 1 by h. 1 by h1 plus 1 by h2 plus and so on up to 1 by hn. Like this, you can write the 1 by h equivalent. 1 by h equivalent. Okay. Yeah. So I'm taking up next problem. Next means problems we are going to take up on this one. Please complete it quickly. Once after completion, please kindly raise your hands. Yeah. So let's say next slide. As we are not using that formula, can we stop studying that? As we don't use that formula, can we stop studying that? Please tell me. Huh? What I said? That formula will be used for a two machine system, I said you. Is it the mean to say we'll stop studying the formula? Go through it, please. It's a very, very simple question to answer. Question. Look here. A synchronous machine rated for 100 MVA has the inertia constant H 5 megajoule by MVA. What is its inertia constant on the base of 150 MVA? So this is one model we can experience in the examination generally. He will give H value on certain base, and he is asking to find the H value on a different base value. Very simple, very simple. Even though you are changing the base value, the kinetic energy stored in the rotor should be remain same. Kinetic energy G into H value with old base and G into H value with a new base must be equal. Okay, that's a rule what we have to follow. Let's say in the solution first. G old 100, H old value 5 megajoule by MV. And G new how much? 150, and H new is how much? Okay, so as we know the principle, G new H new value is equals to G volt into H volt, G volt into H volt. So I can write H new is equals to G volt into H volt by G new is 150. G new is 150. If you calculate this, you get this like 3.333 seconds. That's a H. 3.333 seconds, and your answer is obviously B. Your answer will be obviously B, we can say. Okay, done. Next problem we are going to take up, next model. Go through this one. See, a power station A has 6 identical generator sets. A power station A has 6 identical generator sets. Again, you are asking me how the units are seconds means how can I say, Mr. Anonymous attendee? Have you studied the previous class notes? Have you studied the previous class notes? I've explained you clearly how we are going to get seconds there. Yeah, look here, look here. A power station A has 6 identical generator sets, each rated at 60 MVA and each having an inertia constant of 6 megajoule by MVA, or you can say 6 seconds also. 6 megajoule by MVA or 6 seconds. Okay. The corresponding data for the second station B is 5 sets, each of 200 MVA and 2 megajoule by MVA. If these two stations are very close together at one end of long tie line, these two stations both are located closely at one end of the long tie line. Calculate the inertia constant of single equivalent set on the base of 100 MVA. On the base of 100 MVA. Okay, right. So let's take the two stations here. I will show in the next slide. Showing the next slide. Two stations. First station is having 6 generators. 6 generators like this. Yeah. So what will be the rating of each generator here? I'll call it G1, 60. 60 MVA will be the rating of each one. What is the H value? 6 megajoule by MVA, or you can say seconds. That is station A. Station B, 5 sets, means 5 units. 5 units like this. Rating of each one means G2, 200 MVA. 200 MVA. H2, 2 seconds. H2, that is 2 seconds. Next one. See, these two are these two are very close together and connected at the one end of long tie line. For example, this is a long transmission line you have, or long tie line. At one end of this long tie line, these two stations are connected in this manner. All of you getting this one? This diagram? Please tell me. All of you getting this diagram? This is station A and this is station B. Tell me, please. Tell me. What is kinetic energy of station A? What will be the kinetic energy of station A? Tell me, please. Kinetic energy of station A means you have 6 units here. Each one will have G1, H1, G1, H1, G1, H1 like that, 6. Then all these 6 are in swinging together. Then what is the kinetic energy of whole power station? 6 times of G1, H1. 6 times of G1, H1. What about station B? 5 times of G2, H2. 5 times of G2, H2. I'll write here. Kinetic energy of station A. Kinetic energy of station A. It is GA into HA equals to 6 times G1, H1. So 6 times G1, H1 is again 6. So how much you are going to get? 36, 360 into 6. How much? Tell me this number, how much? GA into HA number? 2160. 2160 megajoules. 2160 megajoules. Next, what will be the kinetic energy of station B? Because in the station B you have 5 units and all the units are swinging together, definitely, because all are connected to the same bus bar, closely located. Then the kinetic energy GB into HB will come to be 5 times G2H2. 5 times. What is G2 number? 200. H2 number 2. So it will come to be, I think, 2000. Is it so? 2000 megajoules. 2000 megajoules. Now, could you please tell me, how will be that station A and station B? Station A and station B, swinging or not swinging? Station A and station B, whether these two are swinging or not swinging. Swinging. Again, these two are swinging together. You write here. Stations A and B are very closely located. Very closely located. So these are assumed to be swing together. These are assumed to be swing together. Assumed to swing together. So if that is the case, G equivalent into H equivalent value. G equivalent into H equivalent value will be equals to GAHA plus, you can write this GB into HB. GAHA plus GB into HB. So you can write now GAHA 2160, GBHB 2000. So it will come to be 4160 megajoules. 4160 megajoules. And what is the equivalent rating of single unit given? Look here, calculate the inertia constant of single equivalent set on the base of 100 MVA. Means he is saying the G equivalent value equals to 100. As G equivalent equals to 100 MVA, we can write H equivalent value as 4160 by 100 units will be megajoule by MVA. So it will come 41.60 megajoule by MVA. You can write, else you can write this as seconds. You can write that as seconds. Yeah. So this is again another model in the examination, we can say, with respect to kinetic energies and all. Another model. So I am taking up one more problem, one more numerical problem in the next slide. Next slide. Go through this one. Yeah. See, a synchronous generator is connected to a synchronous motor. Yeah, any unit you can use for H. You can use any unit for H. Either it is megajoule by MVA or seconds, or you can write this megawatt second by MVA, or you can say per unit megawatt seconds. Any unit you can use. Any unit you can use for the H. Any unit we can use. All the units are equivalent. All units are equivalent. It's not the thing, Shubham. It's not the thing. So their values are almost same. That's why they are swinging together. It's not the case, right? I didn't discuss about values to you at all. Huh? I didn't discuss about GH value, M value. If M values are equal, swinging together. M values are not equal, not swinging together. The type of thing I didn't told to you at all, right? Irrespective of M value, irrespective of H value, irrespective of rating, if identical means like machines are connected to same bus bar, we say these are swinging together. Okay, not with respect to the GH what we have calculated. Yeah, let's move. Yes, look at this question once. A synchronous generator connected to synchronous motor through network of reactances. The ratings of both machines are given below. Generator 100 MVA, H value 4 seconds, 3000 RPM, 0.8 power factor lagging, 50 Hz. Motor 80 megawatt, 3 seconds, 1500 RPM, 0.9 lagging, 50 Hz. If the system is converted into SMIB, then what is the inertia constant H of SMIB on the base of 50 MVA? On the base of 50 MVA. Okay, attempt to do this one. I will come back within 1 minute. Attempt to do this. Yeah, sorry, I'm really sorry. See, in this question given, we have one generator here connected to one synchronous motor. Like this, we have one synchronous motor. Okay, let's write the ratings of these things. First, generator 100 MVA, 100 MVA for the generator. Next, you have H value 4 seconds. Don't bother about remaining. Don't bother about remaining. Frequency. Frequency is one thing what you have to respect, a 50 Hz frequency. 50 Hz frequency. Just you should take up the G, rating of machine in MVA, H value. That's it. Okay, motor you see, motor. He said power rating of motor here. Right? He said here, power rating of motor, that is 80 megawatt. Power rating is 80 megawatts. But we need to have that rating in terms of MVA, right? We need to have that rating in terms of MVA. Yes or no? Right. So, to convert this into MVA, we should check what is the power factor given in the data. Power factor is 0.9. Power factor of this is 0.9. Okay. Now, what is the G of this one? What is the G of this one? Power rating by cos phi, you can say power rating by cos phi. So it is 80 by 0.9 MVA. 80 by 0.9 MVA. So it is G2 you call. This number you can call G1 and this is H1. Can you tell me what is G2? 80 by 0.9, how much? Anybody done? 88.88, good. 88.88 MVA. Fine. What is H2 here? What is H2? Given in the data already, I think so. What is that? 3 seconds. 3 seconds. Okay, let's read the problem once again. If the system is converted into SMIB, so he is asking us to convert this 2 machine system into a single machine system connected to infinite bus bar. Like this, he is asking us to convert. And he is asking to know what is the value of H. What is G equivalent value given here? 50 MVA in the data. G equivalent given is 50 MVA. And how much is the H equivalent value? That we have to calculate. See how this generator and motor will be here. Whether these 2 machines are swinging or not swinging. Whether these 2 machines are swinging or not swinging. Not swinging. So if these 2 are not swinging together, what you should say? 1 by M equivalent equals to 1 by M1 plus 1 by M. Else 1 by G equivalent H equivalent equals to 1 by G1 H1 plus 1 by G2 H2. By using that, we have to calculate H equivalent. That's it. Okay. Yeah. So let's take in the next slide here. The 2 machines given are not swinging together. Machines given are not swinging together. Not swinging together. Okay. So in that view, 1 by G equivalent H equivalent value is equals to 1 by G1 H1 plus 1 by G2 H2. Okay, 1 by, what is G1 H1? G1 number 100, H1 number 4. So it is 100 into 4. Okay, plus 1 by G2, 88.88. And what is H2? That is 3. 3. Okay. And 1 by G equivalent is 50. H equivalent we don't know. So that we have to calculate. Yeah, you please calculate the value of H equivalent from this. Please calculate the value of H equivalent from this one. It's very simple, Vedant. If the real power rating is given, else I'll write some relations here. If you have, just follow. Apparent power S equals to P into cos phi. Okay. Sorry. Real power P is equals to apparent power into cos phi. Apparent power into cos phi. Apparent power S is nothing but our rating. So P by cos phi will give rating of machine in terms of MVA, right? That's it. That's the way of calculating the G in the question. Anybody? H equivalent. G equivalent is given in the data. Srikant, please read the problem. 3.2 seconds. You'll get this number, 3.2 seconds. That's the value of H equivalent number, 3.2 seconds. Fine. That you can type in the blank or you can choose the option. Depends upon the question. Okay. Let's take one more variety of problem here. One more variety of problem. I'll move in the next slide. Why not swinging? We discussed yesterday. Generator and motor not swinging. Huh? Without reading previous class, if you attend the next class, it will be a bit difficult to understand. I said in the starting class itself. Okay, let's take one more problem. Okay. So I'll take in workbook. Yeah. So I'm taking up the first problem here. First problem. Go through it. First problem I am taking up. Go through this question. A 50 Hz 4-pole turbo alternator, 20 MVA, 13.2 kV, has inertia constant H is equals to 9 kilowatt second by kVA. 9 kilowatt second by kVA. Find the kinetic energy stored in the rotor at synchronous speed. Find the kinetic energy stored in the rotor at the synchronous speed. Okay, simple question. Find the accelerating torque. Next, if the shaft input less the rotational losses is 26,800 metric HP and electrical power developed is 16,000 kilowatts. Angular acceleration in degree by second square is how much? Angular acceleration in degree by second square is how much? Okay, do that. Attempt to do this one. What to take? He given connected through reactances in the sense, or simply you have network of reactances. Just reactance network you can consider. Then why those other data were given, Alan, to confuse you? To confuse you, they have given the other data, 1500 RPM, 3000 RPM, all this. So you no need to bother about other data. Yeah, let's move ahead with this problem. We have a 50 Hz alternator, means frequency of system is 50 Hz. And we have a 4-pole machine. 4-pole machine. What is the rating of machine? Means G value 20 MVA. G value 20 MVA. Okay. Inertia constant H number, how much? 9. 9 kilowatt second by kVA. Else you can write simply seconds also. I said 9 kilowatt second by kVA. Okay. What is the kinetic energy stored at synchronous speed of rotation? Kinetic energy stored at synchronous speed of rotation. What is that formula? Simply G into H, right? Yeah, one more thing. Kindly listen. Kindly listen. This is the amount of kinetic energy stored. Kinetic energy stored at synchronous speed only. G into H value. At any other speed other than synchronous. Other than synchronous speed, what formula you have to use? Half J omega S square. Half J omega square. That's the formula to find out the kinetic energy at any other speed. But at what we call synchronous speed, it will be G into H. How much is that number? 20 into 9. 20 into 9. That will be 180 megajoules we can write. 180 megajoules. Because this 20 is in mega, na? So we are going to get that units in mega. So it will be megajoule. That's the kinetic energy stored. Next one. Next one. Next part of problem, kindly observe. Find accelerating torque. Accelerating torque means TA. Accelerating torque calculation. TA. Accelerating torque TA. Look here, look here. Shaft input less rotational losses is 26,800 metric HP. Kindly observe here. Kindly observe. See, for example, if it is some generator we have connected to some shaft associating turbine, something like this, right? Associating turbine, something like this we have. Look all of you what I'm saying. See, whenever we give some mechanical input to this RPS, you see, say simply mechanical input. Observe my words, observe my words. Whenever you give mechanical input to that turbine, turbine is getting rotated. We have some rotational losses. Listen carefully, listen carefully. Rotational losses. For example, I'm giving this input, let us say 100 kilowatt. I'm giving that input as 100 kilowatt. There is a rotational loss of 2 kilowatt, let us say. There is a rotational loss of 2 kilowatt. What is the net mechanical? What is the net mechanical power to be converted into electrical? What is the net mechanical power to be converted into electrical? That will be 98 watts. 98 kilowatts. 98 kilowatts. See, whatever the 98 kilowatts you are saying now, that I am going to say as shaft input less rotational losses. Shaft input less rotational losses means from the actual input we are removing the rotational losses, means that is the resultant mechanical power to be converted into electrical or available for the conversion into electrical form. I think all of you have understood the terminology what they have given in the question. Have you understood the terminology? Tell me, I need your response, please. I need your response. So I can say net mechanical input, nothing but PS, you can write simply to be converted into electrical. That value was shaft input less mechanical losses 26,800 metric HP. 26,800 metric HP. Very simple, very simple. I am explaining again. Ashish Raj, just listen here. We are giving some mechanical input, steam input. Okay. In that input, some amount is lost in the form of rotational losses. For example, 100 kilowatt input you are giving, 2 kilowatt is lost. What is the resultant mechanical input to the, resultant mechanical power to be converted into electrical? What is the resultant mechanical power available to be converted into electrical? Means that is the difference of the two, right? 100 minus 2, that means 98. In the problem, what they said is, shaft input less rotational losses means from the shaft input given, they are removing the rotational losses, deducting the rotational losses. After deducting it, the power is 26,800 metric HP. The meaning of this is 26,800 metric HP is a mechanical power available to be converted into electrical. Mechanical power available to be converted into electrical. Is this clear for all? Please tell me. Right. What do you mean by 1 metric HP in terms of watts? 1 metric HP in terms of watts. Anybody, please tell me. What is that 1 metric HP? This is 735.5 watts. It's not 746. It's not 745 or 746. It will be 735. 735. Okay. So this is metric. Whereas British HP, 1 BHP, it will be 745.5, or you can say 746 watts. 746 watts. That difference you have to observe. See, in the exam, if you said simply HP, which HP we have to consider? British HP. We have to consider it as British. But in the problem given, he said specifically it is metric, American standard. So we have to take that 1 HP as 735.5 watts, right? So it's American standard, metric or American standard, you can say. Metric or American standard. And this is a British standard. British standard. Okay. Now you convert that into watts. I'll say in the next slide. PS is equals to 26,800 into 735.5 watts. 735.5 watts. You say this in megawatt if possible. Kindly tell this number in megawatt. How much in megawatt? How much is in megawatt? Shaft input minus losses should be output power. It's not output power. Vasistha, what I said? Shaft input you have, rotational losses we have removed, means that is the net mechanical power available. Net mechanical power available to be converted into electrical. It's not electrical power, right? Okay. You please tell me this number, how much? In megawatt, 19.7 megawatts. Good. 19.711 megawatts. What is electrical power output from the generator? Electrical power output from the generator, you can call it is PE. How much is that number? How much is electrical power? 16,000 kilowatts. You'll have this number 16,000 kilowatts. Else you can call 16 megawatt. 16 megawatt. Now we calculate the accelerating power, PS minus PE. Accelerating power, PA is equals to PS minus PE. This number will come 3.711 megawatt. 3.711 megawatts. I think all of you getting this? 3.711 megawatts. Next, he's asking about accelerating torque. Accelerating torque. See, after knowing this accelerating power, what is the relationship between power and torque? Relationship between that power and torque is P is equals to T into omega. Torque into omega is power. Okay. So if you want this acceleration, so you say accelerating power equals to accelerating torque into omega. From that one, you try to find out that accelerating torque, which is nothing but TA by omega. So I'll say in the next slide, accelerating torque, TA equals to accelerating power by omega. So now you substitute these things, PA is okay, but that omega we should keep in the form of mechanical. Omega we have to keep in the form of mechanical. So you have to keep 2 pi n by 60. 2 pi n by 60. Let's substitute the numbers. PA 3.711 mega. I'll keep that mega here. 3.711 into 10 power 6. Okay, by 2 pi. What is n? N means you take synchronous speed only. N means you consider that as synchronous speed only. What is synchronous speed of machine? How many poles you have for the machine? 4-pole machine it is. For example, you see, as if a 4-pole machine you have, the synchronous speed Ns is equals to 120 F by P. So it will be 1500 RPM. We have to substitute the speed as 1500 RPM. Okay. So let's take here. So 1500 RPM by 60. 2 pi ns by 60. It will be in the form of Newton meter. That will be in the form of Newton meter. Yeah. Kindly get this number. Kindly get this. How much? We are calculating mechanical torque only, right? Mechanical torque. It will be 23.656 kilonewton meter. 23.625. 23.625 kilonewton meter into 10 power 3 you are going to get. Chandan Chetri, please cross check your answer. Chandan Chetri, please cross check your answer. Approximately you get like 23.625 kilonewton meter. Accelerating torque. Okay, let's look at the one more thing here. In the same problem. Anymore? That's it. Okay. The angular acceleration in degree by second square is asking. The angular acceleration means which angle is that? Is it electrical angle or mechanical angle? He didn't mention anything. Simply asked degree by second square. So you consider that as electrical. See, as you know from swing equation, angular acceleration calculation. Angular acceleration calculation. We know from swing equation. You can see m d square delta by dt square is equals to accelerating power. We need angular acceleration means d square delta by dt square value only we have to calculate. D square delta by dt square value is nothing but accelerating power by m value. Accelerating power by m value. M value. Okay? Yeah. Kindly observe. Kindly observe. What units you need? What units you need? Electrical degree by second square we have to get. Electrical degree by second square we have to get. Okay. Now, already PA is in megawatts. So M what we have here, we have to substitute that in the form of electrical degrees. Okay. What is the formula for M? What's the formula for M? 2GH by omega S is the formula. Else you write 2 into GH by 2 pi F. 2 will be cancelled out. And you write this GH by in place of pi you keep 180 F. GH by pi instance 180 F. And this will come to be megawatt second square by electrical degrees. Megawatt second square by electrical degrees. All of you getting this one? Megawatt second square by electrical degrees. Substitute the numbers. Substitute the numbers. Calculate m value first, then you go for the calculation of that PA. Sorry, that d square delta by dt square. G, what's the rating of machine? G, 20. Okay. 20. What is H value? Check that H value. Anything given? 9. Okay. 9 by 180 into F is 50. So it is megawatt second square by electrical degree. Okay. So now you can take this is 180 cancel, it will come 1 by 50. And if you go into that d square delta by dt square formula, accelerating power 3.711 by 1 by 50, it will come in the terms of electrical degree by second square. Kindly get this one. How much? Get this number. How much? Calculate properly. Calculate properly. 185.57. 185.57 electrical degree by second square, you can say. Electrical degree by second square. Okay. For example, same as previous question. Same as previous question. I am asking you, what will be the rotor body acceleration in mechanical degree by second square? What is rotor body acceleration? Body acceleration in mechanical degree by second square. Tell me please, what is that? How to calculate that in mechanical degree by second square? It won't be same. It won't be same. It won't be same. Because number of poles is not equals to 2, right? Number of poles is not equals to 2. So you don't get this number as it is. But accelerating power will be remain same. The change we are going to get in m value. Change we are going to get in the value of m. In the value of m. That we have to discuss now. That we have to discuss. Yeah. So I am moving in the next slide. Kindly observe here. Same question I repeated what I said in the previous slide. Just as a solution, you said rotor body, na? Rotor body. So let's use this terminology. D square theta by dt square value is asking us to calculate. It is PA by M. Mechanical degree by second square, we need the answer. Where already you know PA 3.711 megawatt. Keep that. What is M value? M value 2 into GH by omega S means 2 into GH by omega S is 2 pi ns by 60. 2 pi ns by 60. And 2 will be cancelled out. You can write now GH by pi into ns into 60. GH by pi into NS into 60. In place of pi, you keep 180. In place of pi, you keep 180. So it will come in the required units. Please complete it first. Please kindly complete it first. Complete this slide first. Can I move? So M will be equals to GH by, in place of pi, we will keep 180 NS into 60. Okay, so it will be GH by 3NS. Don't remember this formula, just you remember 2GH by omega S only. Units of this will be megawatt second square by mechanical degrees. Mechanical degrees. So how come you say it's a mechanical degree, sir? Because we are substituting this omega S in the form of mechanical. Omega S I am keeping in the form of mechanical. Omega electrically is 2 pi F. Omega electrically is 2 pi F. Omega mechanically is 2 pi N by 60. And the pi I replaced with 180. Pi I replaced with 180. So I am going to get this in mechanical degree. So substitute the values. G 20, H 9, mega in the units. Mega is already in the units. 3. Synchronous speed 1500 RPM. 1500 RPM. Okay, you calculate this number if you want. Then directly you can say acceleration d square theta by dt square is equals to 3.711 by 20 into 9 by 3 into 1500. Okay, you calculate this value. It will come in mechanical degree by second square. Tell me please. 92.775. 92.775 mechanical degree by second square is a way how to calculate the acceleration in different units, electrical as well as the mechanical. Electrical as well as the mechanical. Okay, so I will be taking up one more problem. So it's a previous gate examination question. Previous gate question. Go through it. Just write the data what they have given. Just to write the data what they have given. Look here. See, a three-phase, two-pole 50 Hz synchronous generator has a rating of 250 MVA, 0.8 power factor lagging. Okay, rating of generator is given in terms of MVA directly. MVA. Of course, they have given power factor. If it is needed, we will use, else you neglect it. Kinetic energy stored in the machine at synchronous speed is 1000 megajoules. GH value directly given 1000 megajoules. Okay, next. The machine is running steadily. Look here, steadily at synchronous speed and delivering 60 megawatt power at a power angle of 10 electrical degrees. If the load is suddenly removed, assuming the acceleration is constant for 10 cycles, the value of power angle after 5 cycles is dash electrical degrees. Okay, just we will write each and every term what they have given in the question. What they have given in the question. Kindly go through it. Look here. So we have a three-phase, two-pole, 50 Hz alternator. 50 Hz alternator. Okay. Next, rating G. G is equals to 250 MVA. Power factor, he said 0.8 lagging. I'm saying again, if it is needed, we'll use, else we no need to have it. Kinetic energy stored in the rotor at synchronous speed is given 1000 megajoules, and this is nothing but the value of G into H. That is nothing but the value of G into H. Okay, next. See, look here. Initial condition I am saying. Initial state of the system. This is the generator connected to some load, whatever it is. Look all of you here. What is the load demand he said? What's the load demand? 60 megawatt, na? 60 megawatt is a load demand. Yeah, all of you listening to me? All of you listening to me? Yeah, good. 60 megawatt. See, if the electrical power output is equals to 60 megawatt, what should be your mechanical input? If electrical power output is 60 megawatt, what should be the mechanical input? That will be again 60 megawatt, right? Because he said that the rotor is rotating at synchronous speed constantly. Rotor is rotating at synchronous speed constantly. Then obviously the mechanical input and electrical output both are exactly equal. We can say this number as 60 megawatt only. And he is saying that the angle is going to be maintained as constant at 10 degrees. Angle is going to be maintained as constant at 10 degrees. That is our initial rotor angle, delta naught, you can say 10 degrees. Okay, now load is suddenly removed. Means we have removed this load suddenly. Means obviously the electrical power output, what you have initially 60 megawatt, now after removing that load, electrical power output will fall down to 0. Electrical power output will fall down to 0. See this statement. Assuming the acceleration is constant for 10 cycles. What's the meaning of that? What is the meaning of that? Assuming acceleration is constant for 10 cycles. Accelerating power is constant for 10 cycles. Accelerating power means what? PS minus PE. That is maintained as constant for 10 cycles after removing load. After removing the load. Okay, next thing. He's asking that what is the value of power angle after 5 cycles? After 5 cycles. Initial power angle how much? 10 degree. And obviously after the this removal has been occurred, you may expect that the angle is increasing. So angle will increase from 10 degree. Angle will increase from 10 degree and it will reach to some angle at 5 cycles. What is that angle that you have to print here in the option, in the blank? Clear? Yeah. So let's move ahead. I'll tell you like this. So load removed. So assume that at time t equals to 0, load got disconnected. Load got removed. Okay. So this is your generator. And now the load was disconnected. You can say like this. load was disconnected, then what's the electrical power output? You can say 0, and we have some mechanical input as PS, and this is remains at 60 megawatt only. Mechanical input will be remains at 60 megawatt, but electrical power output will be equals to 0. And what is the accelerating power? Accelerating power PA, which is PS minus PE. So this number will be 60 megawatt. Accelerating power PA equals to PS minus PE. That number will be 60 megawatt. And as he said in the problem, up to 10 cycles. What do you mean by 10 cycles here? Up to 10 cycles means what? Anybody? See, anywhere in the examination or in the textbook, anywhere, if you see up to 10 cycles time, or up to 5 cycles time, up to 20 cycles time, if you see this type of terminology, one cycle will be equals to 20 milliseconds for 50 Hz frequency. For 50 Hz frequency, one cycle is equals to 20 milliseconds, means this time will come to be 10 into 20 milliseconds. Else, you can call this as 200 milliseconds, else 0.2 seconds. 0.2 seconds, you can say. Following? So, up to 0.2 seconds from the instant of load disconnection. From the instant of load disconnection, accelerating power is maintained as constant. Maintained as constant. Accelerating power is going to be maintained as constant. Good. Next thing. Now, it is required to find out the angle. It is required to find out the angle at how many cycles? 5 cycles time. 5 cycles time means at 5 cycles time. You write if you want. It is required to find rotor angle at 5 cycles time. 5 cycles time. What do you mean by 5 cycles time here? 5 into 1 cycle is 20 milliseconds. 20 milliseconds, and this number will come 0.1 seconds. That number will come to be 0.1 seconds. Clear? At 0.1 seconds, we have to calculate. Delta with respect to time, we have to know. Delta with respect to time, you have to know. Who will give the relationship between the delta and time? Who is going to give relationship between delta and time? Tell me please. Swing equation. Swing equation is a thing which is going to give relation between delta and time, right? So, as we know the swing equation already, swing equation, m d square delta by dt square is equals to accelerating power PA. M d square delta by dt square equals to accelerating power PA. Else you write d square delta by dt square equals to accelerating power by m. D square delta by dt square is equals to accelerating power by m. Okay? Yeah. Tell me please. Tell me. Can we integrate this equation? Is it possible? Which type of equation is this? I need your response. Which type of equation is this? Is it a linear equation or non-linear? Non-linear. Non-linear we said earlier, right? Why in the sense? Accelerating power equals to PS minus PE, where PE is P maximum sine delta. So it's a function of delta, that's why it is non-linear. But in this present case, accelerating power is constant at 60 megawatt, right? Accelerating power is a constant number to you. As if it's a constant number, d square delta by dt square is a number, is a numerical value. So we can go for direct integration of this equation now, because PA is constant. So you write here, as PA is constant, it is possible to integrate above equation directly. Integrate above equation directly. It is possible to integrate the above equation directly. Okay, fine. So let's take first differentiation, first integration of equation 1. I'm moving to next slide. Please complete it quickly. It is one of the model. It's one of the model in the examination we can find. Yes, so I'm taking up in the next slide. Integrate equation number 1 with respect to time. With respect to time, what you will get now? Left side integration will give d delta by dt. Right side you will get PA by m into time plus some constant. You assume it is C1. D delta by dt. Other side you get PA by m into time plus some constant. It is C1. Some constant C1. Next thing. How to get that constant C1? We have to apply initial condition. We have to apply initial condition. At time t equals 0, we call it the equation. At time t equals to 0, time t equals 0, what is d delta by dt? What is d delta by dt at the time t equals 0? Anybody? Anybody tell me? See, what is the formula for d delta by dt generally? What is the formula for d delta by dt? Omega minus omega s, right? D delta by dt formula, omega minus omega s. See, just before load removal or just after load removal also, speed will be remains at synchronous. Speed will be remains at synchronous speed. So I can call omega is equals to omega s. So I can say d delta by dt value will be equals to 0. You write equation better. Omega minus omega s. That will be 0 at the time t equals 0. At the time t equals 0, d delta by dt value will be equals to 0. Okay. So therefore, from equation 2, at time t equals to 0, what you can write is d delta by dt value was 0. PA by m into time 0. You write PA by m into time 0 plus C1. And how much is the constant C1 you can get now? 0. So the equation 2 will come simply like d delta by dt equals to PA by m into time. Okay. Yeah. So I am moving in the next slide. Going to next slide. So if you have completed, it's well and good. Yeah. So taking up the next slide. So therefore, equation number 2 can be rewritten as d delta by dt is equals to PA by m into time. Again, you take one more integration of that above equation. Integrate above equation with respect to time. Above equation with respect to time. What you'll get now? Delta on the left side, right side of PA by m into t square plus constant C2. This is, you write delta of t, a function of time, delta of t, 1 by 2 PA by m t square plus some constant C2. Okay. Yeah. Now, again, to find out that C2 constant in this equation 3, you have to apply the initial conditions. Initial condition means at the time t equals to 0, delta of 0 is nothing but delta naught. Nothing but delta naught, which is 10 degree. In this problem, it is 10 degree. But don't keep 10 degree. You keep delta naught, which is the initial rotor angle just before disconnection of the loop. Okay. So therefore, delta of 0 equals to 0 plus constant C2. So the constant C2 will come delta naught. Therefore, equation 3, you can rewrite finally. Equation number 3, you can rewrite finally. Delta of t equals to 1 by 2 PA by m times square plus that constant is delta naught. 1 by 2 PA by m t square plus that constant we have as delta naught. So I think all of you getting this. When this equation is valid, when we can use this equation? Tell me please. when this equation is valid. This is valid only whenever accelerating power is constant. It is valid only if accelerating power is constant. With respect to time. With respect to time or with respect to angle, whatever it is. With respect to time, if the accelerating power is constant, then only we can say this is used, means this formula will be used. 1 by 2 PA by M time square plus delta naught. Now, you substitute the values, whatever you know, into this, you will get the answer. Yeah. So I have to move to next slide to give the answer to you. Give the answer. Yeah, I will repeat it. Kindly observe. Correct, Vishnu, correct. For example, Vishnu is asking this type of question. Sir, for example, in the problem, if they said that accelerating power is constant up to 2 cycles, and how much is the power angle value at 5 cycles means we can't do, because he is saying up to 2 cycles only it is constant. In the sense, this formula you can use only up to 2 cycles. Beyond 2 cycles, we don't know whether this formula is valid or invalid. Clear, right? Very simple. Swing equation. md square delta by dt square equals to accelerating power. D square delta by dt square is PA by M. As accelerating power is constant in this case, it is possible to do the integration. But in case of original equation, we said original swing equation, PA is PS minus Pmax into sine delta, which is function of delta, non-linear one. That non-linear equation we can't integrate. But as PA is constant, it is possible to do the integration. Okay, so first integration I have done. After doing first integration, d delta by dt equals to PA by M into time plus the constant C1. How to get this constant C1? Initial condition we have to use. Initial condition means at time t equals to 0, speed is equals to synchronous speed. D delta by dt formula is omega minus omega s, that is 0. After saying that is 0, if you substitute that conditions into 0, PA by M into 0 plus C1. So C1 will be 0. So this won't exist now. So the equation 2 you can rewrite as d delta by dt equals to PA by M into time. You do one more differentiation, you will get this, integration, you will get delta equation. After doing that integration, we got the constant C2. That constant C2 you will get as initial angle delta naught, and this will be the final equation for delta with respect to time. Final equation for delta with respect to time. Yeah, so let's move ahead. Now, at the time t is equals to, first you have to think about the remaining values also in this one, right? Where accelerating power how much? 60 megawatts. Okay, what is M? What units you have to consider for M? Is it electrical or mechanical? That tell me first. M, electrical or mechanical? Electrical, because we are thinking about electrical angle now. Electrical. Which units? Radian or degree? Degree. Electrical degree in the sense GH by 180F megawatt second square by electrical degrees. So what's the rating of machine given? Already GH value directly given, right? GH value directly given, I think 1000. GH value they said directly 1000 by 180 into frequency, it is 50. So it will be megawatt second square by electrical degrees. So now if you calculate that PA by M from this, PA by M you calculate from this one. So it is 60 by 1000 into 180 into 50. You do your own cancellations. 0 zeros will be cancelled, 0 0 will be cancelled, and 18 5s, I think 90 into 6. So it will be 540. Is it so? Is it you get? It will be in electrical degree by second square. Electrical degree by second square. Is it 540 PA by M? PA by M. Yeah, good. So now at the time t equals to 0.1 seconds, delta of 0.1 seconds is equals to 1 by 2 PA by M times square means 0.1 into 0.1 you can write times square plus angle 10 degrees. Delta naught is 10 degrees. And you see 0.1 square means 0.01. So it's 5.4 by 2. 5.4 by 2 means 2.7. 2.7 degree plus 10 degree, it's 12.7 degrees. 12.7 electrical degrees we are going to reach. 12.7 degrees. That's the angle at a time 0.1 seconds or at 5 cycles time. 5 cycles time. That M we have to use in a common sense. M we have to use in a common sense. Is it electrical or mechanical? What you are calculating? Angle. Electrical angle. I have to keep electrical. Okay, degree or radian. Because I am keeping delta naught in degree. Na? Delta naught I am keeping in degree. Let's take that M also in degree. That's the way of understanding it. Okay, same question. Same question. Same question. Okay. Same as previous question. Same as previous question. What is the rotor speed at the end of 5 cycles? End of 5 cycles. In RPM. In RPM, how much is the rotor speed at the end of the 5 cycles? Observe this one. How 20 milliseconds? 1 cycle equals to 20 milliseconds. How? Time period of 1 cycle is 1 by 50 hertz, right? Time period of 1 cycle is 1 by 50. That's 20 milliseconds. Time period. 1 cycle time period is 20 milliseconds. Okay, fine. Look here. Same as the previous question. Now the question is, what is the rotor speed at the end of 5 cycles in RPM? Means you have to find the N value, rotor speed value. To do that, I am writing swing equation only. Listen all of you. I am writing the swing equation only. Yeah, I'm writing from swing equation. From swing equation, we have this form, right? M into d omega by dt is equals to accelerating power. M into d omega by dt is equals to accelerating power. This is one type of equation. And what is d omega by dt? Pa by m. D omega by dt, that is equals to Pa by m. And that omega, what we have, omega, that you substitute as 2 pi n by 60. Omega, you substitute that as 2 pi n by 60. So, d by dt of 2 pi n by 60 is equals to accelerating power by m. And this 2 pi by 60 is constant number, take it out. 2 pi by 60 is constant number, take it out. You send to the other side. The 2 pi by 60 you send to the other side. You can get like this. dn by dt is equals to Pa by m into 60 by 2 pi. Pa by m into 60 by 2 pi. That's dn by dt. dn by dt. Next thing. After 5 cycles, end of 5 cycles, both are same. He's asking the calculation at the instant of 5 cycles. That's it. Simple. Is it possible to integrate this equation? Tell me please. Whether this Pa is constant with respect to time or variable with respect to time in the present discussion. Constant. So if Pa is constant value, then direct integration can be done. Direct integration can be done for the above equation. can be done for above equation. So that integration, if you do, you'll get here again PA by M into 60 by 2 pi into time plus some constant C3. This is N of t, you write. Speed as a function of time. Speed as a function of time. PA by M into 60 by 2 pi into time plus some constant C3. How to get that constant C3? We have to apply initial condition. So at time t equals to 0, what is N of 0? N of 0 is nothing but synchronous speed only, right? N of 0 is nothing but synchronous speed only. You call this is equation. We follow that numbering 4. Equation 4. Okay. So from equation 4, from equation number 4, N of 0 is equals to PA by M into 60 by 2 pi into 0. 60 by 2 pi into 0 plus that constant C3. So from this you can call constant C3 equals to N of 0 means it is synchronous speed Ns. Constant C3 will be equals to synchronous speed Ns. Now you substitute that in the equation 4. That you substitute in equation 4. Right? So let's write here. So therefore, equation number 4 can be rewritten as speed as a function of time equals to 60 by 2 pi into PA by M into time plus synchronous speed Ns. This is the other way, other equation which will be used to calculate the speed. This is also very important equation. It is one of the untapped area of asking the speed. It is one of the untapped area in the examination of asking the speed. Till now, they didn't ask any question regarding the speed calculation. Speed calculation. Okay? Yeah. Simple. Tell me, please. Tell me in this particular one, what units we should use for PA by M? Anybody? Tell me, anybody. What units we should use for PA by M here? Is it in electrical or mechanical? That tell me first. Which units you should use? Mechanical. Okay, good. Radian or degree? Radian or degree? Radians. Mechanical radians. And this PA by M must be in the manner of mechanical radian by second square. It should be in the manner of mechanical radian by second square, such that you should select the M value. Such that we should select the M value here. Okay. So I will be choosing that M here first. M. Original formula for M. Original formula. Electrical, mechanical, anything. Original formula is 2 into GH by omega S. Means 2 into GH by omega S value. Omega S equation. 2 pi Ns by 60. This will be in megawatt second square by mechanical radians. Megawatt second square by mechanical radians, or megajoule second by mechanical radian, you can write. Okay, you manipulate this thing and you calculate this M value. 2 into GH is given 1000. Mega already taken into units. Mega we have taken already into units by 2 pi. What is synchronous speed? 3000 RPM. Because it's a two-pole machine. It's a two-pole machine. So it will be 3000 RPM. 3000 RPM by 60. You please calculate this M value. Tell me please how much M value. Make it quick please. 6.369. 6.369 you are saying. Megawatt second square by mechanical radians. Now directly you can move into that equation. Okay, and you write the numbers. So speed you have to calculate at the end of 5 cycles means at the time t equals to 0.1 seconds. At the time t is equals to 0.1 seconds. 0.1 seconds. N of 0.1 is equals to 60 by 2 pi into accelerating power. How much is accelerating power? We have calculated 60 mega by m. M is 6.3639. Okay, into time 0.1 seconds. And what is the synchronous speed? 3000 RPM. 3000 RPM. All units will be RPM again. All units will be RPM. Yeah, you please tell me this speed, how much? Right? How much is the speed? So it will be 3009 approximately. You will get this number as 3009 RPM. 0.003 something will get compromised to 3009 RPM. Now again, this formula what we have written here, N of T formula, this is valid only whenever accelerating power is constant. Valid only if accelerating power is constant. A is constant. Please remember these two equations. Please remember these two equations. There is a good possibility of getting problem in this area. Mechanical radian Y means we have to get the what we call answer in terms of RPM. We have to get this one in terms of RPM. The answer differs when we use M value without decimal. It may not be a great difference, Sunanda. It may not be a great difference. You don't get it. Great difference you may not get. Okay. In both, I think so. In gate, there's a probability of getting question of this type. Okay. So I think the problems what you have discussed till now are sufficient with respect to this area. This is one area where we have to concentrate. So let's say in the next slide, the next heading, simply I am taking different systems. Just for the sake of heading only, I am writing this one. Different systems. Number one, I can say single machine system. Single machine system. Anywhere in the stability analysis further, if you listen this word as a single machine system, you should not be in an impression that we have only one generator or only one machine, right? What you have to understand, if you look this single machine system means a single machine connected to infinite bus bar. Single machine connected to infinite bus bar. That's the meaning here, right? Single machine system is nothing but single machine connected to infinite bus bar. This is one case. Second case, sometimes the people will say two machine system. And the next one you can say multi-machine system. Number of machines you can say. Multi-machine system. Single machine system, two machine system, or you can say the next one is 3003 is not fine. Sunanda, please do the calculation once again. Please kindly do the calculation once again. Yeah, these are different types of systems. We have single machine, two machine, and multi-machine. Next. What are the various methods? To do the transient stability analysis? First method already I indicated in the discussion of the swing equation itself. That is nothing but simply solve the swing equation by using numerical integration techniques, right? For a given disturbance, and try to know how the delta is going to change with respect to time. Based on the delta variation, we are capable to decide whether the system is stable or unstable for a given disturbance. That is one technique of doing the transient stability analysis. Okay, I'll show in the next slide. Methods to do transient stability analysis. Transient stability analysis. Methods to do the transient stability analysis. First and foremost method we are saying numerical integration of swing equation. Integration of swing equation. So by solving the swing equation, delta versus time, so-called swing curve, delta versus time curve is going to be called as a swing curve. Swing curve can be constructed. By constructing the swing curve, we are capable to say whether the system is stable or unstable here, right? By solving swing equation, the swing curve can be constructed. Swing curve in bracket delta versus time curve can be constructed. And based on it, the system stability can be decided. The system stability can be decided. Stability can be decided. Okay. The system stability can be decided. This one thing. But main disadvantage of this one, listen please. Main disadvantage of this method is laborious. So we have to spend a lot of time. To get the solution of the swing equation. But anyhow, in the present days, the people are using this only because we have sophisticated mathematical technologies, maybe MATLAB or Python programming, machine learning, whatever it is. See, by using these techniques, we are capable to solve the swing equation within one click. With a click, we can solve, and we can solve it for different cases also. But anyhow, the people will say, in the olden days, this method is a bit laborious and time consuming to tell whether the system is stable or unstable, right? So it's a laborious method. It is laborious, means a bit difficult one, and time consuming. To make a comment on the system stability. Yeah. So in order to reduce that difficulty in the analysis, as well as to tell whether the system is stable or unstable within very less time, the people have proposed the second method as equal area criteria method. So where after the creation of disturbance, after taking up the disturbance, we are going to check the accelerating area, deaccelerating area, right? And based on that, we are going to decide whether the system is stable or unstable. Yeah. So I'll say the next method here, that is second one. Second one is equal area criteria. I will call this one shortly EAC. I will call this one EAC. Equal area criteria. So it is a type of graphical approach. It's a graphical approach It's a graphical approach to decide or analyze the system stability. It's a graphical approach to decide the system stability, or you can say to analyze the system stability. Yeah, fine. Next. But there is one disadvantage for this method also, equal area criteria method. We can do the stability analysis. Transient stability analysis only for single machine system here. By using equal area criteria, you are capable to do the transient stability analysis only for single machine system. Single machine system means single machine connected to infinite bus bar, right? So, but this method is applicable. Only on SMIB. Single machine connected to infinite bus bar. Yeah, I'm asking one very simple question to you. Can we apply can we apply equal area criteria method on a two machine system? Can we apply this equal area criteria method on a two machine system? Yes, we can apply. We can apply. But what you should say is, listen please. What you should say is, the two machine system should be converted into a single machine system, and then the equal area criteria has to be applied. You have to come. See, the technique, the mathematical technique is applicable only for SMIB. But if you want to apply this equal area criteria on the two machine system, first you convert the two machine system into single machine. Then you go for the application. Okay, right. That statement also helps. Before applying equal area criteria on a two machine system, it has to be converted into SMIB by using combining machines techniques. What here? It has to be converted into SMIB. It has to be converted into SMIB. Yeah, fine. But whereas the step-by-step solution, or you say numerical integration of string equation, it can be applicable on any system, any number of machines, right? Can be applied on any system. Can be applied on any system. Any system. But we have a restriction on the equal area criteria, which is applicable only on the SMIB. Anyhow, according to the syllabus of our examination, we will be continuing with equal area criteria 1. We will be continuing with the equal area criteria to do the analysis. So before moving to this equal area criteria and all, first of all, I want to write what are the assumptions to be taken in the transient stability analysis. First, we'll take assumptions in the transient stability analysis. Then we take the heading as equal area criteria. How we will say system is stable or unstable by using this equal area criteria. What is that method? What is that method first that we'll learn? After learning that, we will see what are the different cases on which we are going to apply this. Okay? Yeah. So in the next slide, I'm going to take a assumptions in transient stability analysis. Transient stability analysis. Assumptions in the transient stability analysis. Fine. Next. First assumption, first and foremost assumption. See, all the time, the first assumption will be the representation of generator. First assumption will be the representation of generator. Just listen to these words. Listen to these words. In case of fault analysis, how you represent a generator? Subtransient EMF source, EG double dash. Subtransient EMF source. Behind its direct axis subtransient reactance, XD double dash. In case of steady state stability, steady state EMF, EG. Behind its D axis, steady state reactance, XD. Whereas in the transient stability analysis, generator, or you say alternator represented as transient EMF, EG dash source. Behind its direct axis, transient reactance. Behind its direct axis, transient reactance. You call it is XD dash. This is a way of representing that alternator, right? So I can show that model like this. So this is the transient EMF, and this is JXD dash. Next one. Second assumption, representation of transformer and transmission lines. These are going to be represented as simple series reactances. Series reactances. We are going to neglect the resistances in the whole system. In the whole system, we are going to neglect the resistances. Right. So transformer and transmission lines. Transmission lines represented as series reactances. Series reactances. Transformers and transmission lines are represented as series reactances. Yeah, you please complete it quickly. I'll move to next slide. We combine n machines together, then we can use EAC. Yes, Vishnu, you can use it, but combining n machines into a single machine may not give a good accuracy to you. May not give a good accuracy. Yeah. Next thing. Third one. Neglect. Losses in the system. Losses in the system. Or assume that network resistances are zero. Network resistances equal to zero. Network resistances we are assuming as zero. That's the assumption. Next assumption. Generally, alternators we have of two types, right? Alternators we will be having of two types. One is a round rotor machine. Next one is a salient pole. Alternators will be of two types. One is a round rotor machine. Next one is a salient pole machine. Generally, in case of salient pole machine, we have a difference between the direct axis and quadrature axis reactances. We have a difference between direct axis and quadrature axis reactances. The difference we are going to neglect now. Means saliency. Saliency in the machine is going to be neglected. Means all the alternators are assumed to be round rotor alternators only. Right? Saliency in alternators was neglected. Or saliency in the synchronous machines also, you can say, in motors also, that will be neglected. Yeah. So I'm showing previous slide. If anybody is still writing, please complete it quickly. Major assumptions are there still to discuss now. Major assumptions we have still to discuss. Damping in the system will be completely neglected. Means the effect of damper bars will be neglected, I can say. The effect of damper bars will be neglected. That's the fifth one. Effect of damper bars. Damper bars or damping. Damping is neglected. Effect of damper bars or damping is neglected. That's the fifth one. Next. Yeah. Sixth one I'm saying. Kindly observe. Yeah, dear, why to use this, sir, when so many assumptions are there, waste method? Okay, you feel it's a waste method. You don't take all these assumptions, try to do transient stability analysis. Don't take all these assumptions. Consider all the things what I said. Attempt to do the transient stability analysis, then you will get the feel of it. Okay? Yeah. Look here. For example, we have an alternator connected to some infinite bus bar, something like this. Just observe my words, what I'm saying, very simple words. It is a mechanical input, here PS. Mechanical input is PS. Listen to me. Initial condition, it's a healthy condition. We have PS and PE values are exactly equal. Operating frequency is 50 Hz. And we have some terminal voltage for this machine. Terminal voltage for this machine, something like VT. Terminal voltage for this machine is something like mod VT. Mod V, you assume. Unfortunately, I'm saying that we had some fault on the system. Look all of it. Whatever the disturbance you considered, is it a fault or load increment, generation increment, whatever it is, Ultimately, listen, ultimately our aim is to know how the delta is going to change with respect to time, right? Our aim is to know how the delta is going to change with respect to time. That's what our aim, by using swing equation or whatever it is for. See, whenever you have a short circuit fault, this electrical power may fall down to zero because there is no path for current flow to the what we call infrared bus, and current will be circulating in this loop only, and we don't have any electrical power transfer. PE value is equals to zero. Because of that, PS minus PE, we have an acceleration for the rotor. Whenever you have that acceleration, this operating frequency will increase now. Whenever you have an acceleration, rotor will rotate at higher and higher speeds. Rotor will rotate at higher and higher speeds. So obviously frequency of operation is going to be increased, we can see. Okay, listen to my words, Generally, in a practical system, practical power plant or practical generators, at the terminal of the practical generator, you observe one frequency sensor. You observe some sort of frequency sensor. What this frequency sensor will do? It will sense the frequency, whether it is a low value or high value, right? It's going to sense the frequency value. Is it low or high? After sensing that frequency, it will give a command. It will give a command for speed governor mechanism. It will give a command for the speed governor mechanism. And what the speed governor mechanism will do? It will try to control the value of PS. It's going to control the value of PS. Very simple words. I am repeating this thing. Kindly observe. We have a frequency sensor. Whenever a short circuit fault occurred, we have a frequency variation also. Frequency variation is there. And frequency sensor is sensing that the frequency is not equals to the 58 frequency. Then it will give a command to the speed governor mechanism such that the speed governor mechanism will attempt to control the PS value. Now tell me, practically speaking, whether this PS is constant or variable with respect to time during disturbance. Whether the PS is constant or variable with respect to time. Yeah, it will be a variable number. It's a variable, right? Govindu, what I said just now. What is the aim of the speed governor mechanism? Speed governor will attempt to maintain the mechanical input and the electrical outputs as exactly equal. Means according to the changes in the electrical output, mechanical input also going to be changed. So this PLC is not constant. It's a variable number with respect to time, controllable value by means of speed governor. But listen carefully. But my aim right now is to study only delta variation with respect to time. So we are assuming that the speed governor mechanism was deactivated. By the way, mechanical input is going to be assumed as constant with respect to electrical power variations. Following all of you, right? I'll write that assumption. What I said just now. Speed governor mechanism. Was deactivated speed governor mechanism was deactivated. That implies PS, mechanical input, is assumed as constant with respect to electrical power PE variations. With respect to the electrical power variations, we are going to assume that PS is constant. Clear? Next one. Next assumption. Kindly observe. See, in similar to this one, generally at this terminal, we'll have some voltage sensor also, right? And whenever that voltage sensor is sensing that voltage is low or high during this disturbance time, it will give a command for what? For the automatic voltage regulator mechanism. It will give a command for the automatic voltage regulator mechanism, and that automatic voltage regulator mechanism will try to control this induced EMF in the machine. It is going to control the induced EMF in the machine. Following all of you, I will repeat the same statement. Very simple thing. Whenever we have a fault, voltage at the terminal of the alternator was fallen down, and voltage sensor is there that has sensed that voltage is very low number, and it is giving a command. It's giving a command for automatic voltage regulator, and this automatic voltage regulator will attempt to correct the excitation. Means attempt to correct the DC input voltage to the rotor. DC input voltage to the rotor. By that way, it is capable to control this induced EMF in the machine to maintain a proper terminal voltage. To maintain a proper terminal voltage, this induced EMF value is going to be controlled. Clear? But whenever this E is changing, you know the equation of P maximum, mod E into, it's a VT, right? It's mod V. Infinite bus voltage mod V by X equivalent. Whenever that E value was changing, definitely P max value will change. Whenever the P max value is changing, obviously the power angle curve peak value will change now. Power angle curve peak value was changing. So P max is variable with respect to time, we can say now. I don't know whether you are understanding this concept or not. Very simple concept. All of you tell me, have you understood this? Yeah. Listen. I am explaining AVR again. Very simple. If you have a short circuit fault, voltage at the terminal of the alternator will fall down to very low value. Automatic voltage regulator will sense it, means voltage sensor will sense it. It will give a command for automatic voltage regulator. And this automatic voltage regulator will control the induced EMF by means of excitation control. It will control the induced EMF. Means I can say that this induced EMF is variable with respect to time during disturbances. If it is variable, obviously P max value is variable during the disturbances. Yes, that we are not going to allow. So I'm not going to allow too many variables with respect to time. We are going to allow only angle variation with respect to time. That's what we have to study. So by that way, I'm going to deactivate this automatic voltage regulator action so that the induced EMF or excitation EMF in the alternator is assumed as constant with respect to disturbances. Right? So I can say that the seventh assumption here, AVR mechanism was deactivated. That implies excitation EMF mod E is assumed as constant during disturbances. So these are various assumptions we are taking up. Yeah. So among all these assumptions, the major assumptions will be mainly neglecting damper bars. Of course, all are required, but major in the exam. Damping is neglected. Speed governor mechanism deactivated. AVR mechanism deactivated. Okay, these are main, very important assumptions to be considered. Okay, so you have a break for 15 minutes. After break, we will be starting with the equal area criteria technique. What's the methodology we have that we are going to start? 15 minutes break. So I have resumed audio video on screen. Resumed my audio video on screen. So let's continue with the equal area criteria technique what we have mentioned, right? Equal area criteria technique. EAC. See this. Yeah, you asked me in the doubt session if you have any doubts in the assumptions. You asked me in the doubt session if you have any assumptions. Sorry, doubts in the assumptions. See, let us go with the swing equation. Swing equation of SMIB. Swing equation for single machine connected to infinite bus bar. M d square delta by dt square is equals to accelerating power PA. M d square delta by dt square is equals to accelerating power PA. Okay. So this I am going to rewrite. D square delta by dt square equals to accelerating power by M. D square delta by dt square equals to accelerating power by M. Right. Now I'm multiplying. I'm multiplying both sides of this equation. Both sides of this equation with the 2 times of d delta by dt. Multiply with 2 times d delta by dt on both sides. On both sides. See, after doing that multiplication, left side will come 2 d delta by dt into d square delta by dt square is equals to 2 times d delta by dt into PA by M. 2 times d delta by dt into PA by M. Like this, we are going to get 2 times d delta by dt into d square delta by dt square equals to 2 times d delta by dt into PA by M. Okay. So I'll show in the next slide. Next slide. Just I'm taking up some small calculation first. I want to know what is this d by dt of d delta by dt whole square. What is this one? D by dt of d delta by dt whole square. See, simple. This d delta by dt is a function of time. D delta by dt is a function of time. So you say it is f square. F square. F square differentiation with respect to time means 2f. 2f. Again, that f is differentiated with respect to time. Na? So you can say it is 2 times of f is d delta by dt. Again, that f d delta by dt was differentiated with respect to time like this. Okay, so this you can get like 2 times d delta by dt into d square delta by dt square. Like this we are going to get. Following all of you? Simple, simple. So my intention is to tell you here, in the previous term, 2 times d delta by dt into d square delta by dt square you have, that you can replace with, d by dt of d delta by dt whole square. So this LHS term you can replace with d by dt of d delta by dt whole square. And remaining term we will keep as it is. I'll call this equation 1. So I'll write equation 1 can be rewritten as d by dt of d delta by dt whole square is equals to 2 times PA by M into d delta by dt. Just we have rearranged those terms. 2 times PA by M into d delta by dt. Next thing. Simple. You do the integration on both sides with respect to time. Just I will show the integral. That's it. Okay. Integrate with respect to time. So this is integral of d by dt of d delta by dt whole square with respect to time is equals to integral 2 times PA by M d delta by dt with respect to time. Right? So you see the left-hand side term, d by dt of d delta by dt whole square with respect to time. See, differentiation and you have integration again. Differentiation with respect to time. And again, integration means it will come to be simply d delta by dt whole square. Clear? Right. So I'll say left-hand side term is simply d delta by dt whole square here. D delta by dt whole square. You look at the right-hand side term. Look at the right-hand side term. If you want, you can cancel it. This dt can be cancelled, and it will come to be integration of 2 times PA by M with respect to delta. 2 times PA by M with respect to delta. Clear? dt was cancelled. And you see in this integral term, 2 is a constant number. M is also constant number. PA depends upon delta. PA depends upon delta. So this you can write as 2 by M integral PA d delta. So this is the value d delta by dt whole square. So from this you can get d delta by dt value nothing but square root of 2 by M integral PA d delta. Right? Square root of 2 by M integral PA d delta. Like this we are going to get the resultant equation what we have derived from this thing. Yeah. D delta by dt equation we have derived till now. Square root of 2 by M integral of PA d delta. Right. Next. I'll tell you what's the intention of this derivation and all. Why we are deriving this and all, that I will tell you. So I'm going to take up some cases here. Case 1, case 2. Just listen. Next slide I'm showing. Case 1. Case 1. See, I'm going to show swing curve. I'm going to show swing curve in the case 1. That axis I'm going to show time axis and delta axis here. This is a time axis. And this was delta axis I am showing. Like this. Delta axis and this was time axis. See, this is the time t0 at which we are having a disturbance. That's the time t0 at which we are having the disturbance. You write it is instant of disturbance in bracket. Time t0 is instant of disturbance. Instant of disturbance. Okay, next. See this. See, up to the time t0, the rotor angle is constant at a value of delta naught. The rotor angle is constant at a value of delta naught. So this is that constant angle we have in the initial condition, which is maintained as constant at delta naught. Okay, delta naught. Next thing. Look here. See, from that instant of disturbance occurrence, I am observing that angle is increasing like this and reaching to some value like this, and then it's falling down and then going high and then falling down again. Like this, the angle is continuously changing. And it is going to be maintained as constant after some amount of time. After some amount of time, that angle is becoming constant in this manner. Okay, look here. This is in one case. Case 1. In the case 2, I'm going to show like this. The case 2. Here in the case 2, I'm drawing case 2, some other case. How is that angle, so-called delta variation with respect to time? If you see delta variation with respect to time, it's a time axis. Okay, so it's a delta axis you have, and delta versus time, and it was a time t0 at which the disturbance is going to occur. This is an instant of disturbance again. You can call in bracket instant of disturbance. See, up to the time t0, you have this angle as delta naught only. Up to the time t0, You have an angle of delta naught here. Okay. Next, starting from the time t naught, it has been observed that the angle is increasing simply in this manner. It was observed that angle was increasing simply in that way. Clear? Angle is increasing in that manner. Fine. Listen. I will ask you very simple question. Don't confuse. Leave all the things what you have in your mind. Leave all the things whatever you have in your mind. If you might have studied something here, forget about it. Just listen. Look here in the first case. The angle is increasing from delta naught, reaching to some high value and coming back, and it's continuously changing like this. And finally, it is becoming constant. Can we say the system is stable or unstable if you get this type of swing curve? Whether the system is stable or unstable? Stable. What is the reason? To say that the system is stable? Simple. The angle is becoming constant after certain time. Whenever the angle is constant, I'll say electrical power output is constant with respect to time. So we have a bounded output. As we have a bounded output, obviously we can say the system is stable. So this we are going to say as a stable swing curve. So in this case, the system is stable. Okay. So in the other case, you observe angle is continuously increasing now. So obviously we can say electrical power output, we can't define it exactly as a constant number. As electrical power output is not exactly as a constant number, definitely we can say if you get this type of swing curve in the analysis, system will be unstable, and this we are going to name as unstable swing curve. Unstable swing curve, you can see. Clear? Next thing, very simple question. Without plotting this swing curve, without thinking about this whole swing curve and reaching to steady state and all, how we can say the system is stable or unstable? That's the question we have to ask ourselves. Okay, how we can say whether the system is stable or unstable without plotting this swing curve, without plotting this complete swing curve what we have up to the time. See, listen. I'm checking this thing here. Initially, angle is delta naught. From there, it is increasing, reaching to some value, and then decreasing. Angle is reaching to some value and then decreasing in case of stable case. Whereas in case of unstable case, always angle is increasing. If you observe this type of trend, obviously we say system will be stable or unstable easily. Just by checking angle, how is that angle? And if the angle is increasing to some value and then falling down, we can say system is stable. Else, if the angle is continuously increasing, we can say system is unstable. Rather than that also, we are going to take up one more. That is, look here. I am asking some value here. Slope of the swing curve, so-called d delta by dt. Slope of the swing curve. Just observe. Pre-fault condition means before the disturbance occurs. How much is slope of the curve here? What is slope of the curve? 0, because it's simple line, flat line. So here d delta by dt number is 0. Next thing. Disturbance occurred. We are standing at this place. What is d delta by dt here? I am asking you, is it positive or negative or 0? That's it. Only these. How is d delta by dt at this point where you are standing? Positive, negative, 0. Positive. It's a rising curve. So d delta by dt number was greater than 0. Now, how is d delta by dt here? Again, positive. It's a rising curve here also. And here also positive. And at this place, how much is d delta by dt? How much is the value of d delta by dt here? That is 0. D delta by dt is equals to 0 at the top point where we have met. Okay, next thing. How is d delta by dt here? It's a falling curve. It is less than 0. How is d delta by dt here? Falling curve less than 0. And here again d delta by dt 0. And here d delta by dt positive. And here d delta by dt 0. D delta by dt negative. D delta by dt 0. Like that, the d delta by dt value was changing. D delta by dt value was changing in case of the stable swing curve. Stable swing curve. Okay, good, good. Next thing. If you look at the unstable swing curve here, unstable swing curve, in the pre-fault condition, before the occurrence of disturbance, d delta by dt number 0. D delta by dt number 0. After the disturbance has been occurred, how much is d delta by dt at the point where we have shown? Greater than 0. How is d delta by dt at this point? Again greater than 0. How is d delta by dt at this point? Again greater than 0. Means observation is that always we are observing that d delta by dt value was greater than 0. Greater than 0. See, from the instant of disturbance occurrence, we try to calculate the value of d delta by dt number. We'll try to calculate the value of d delta by dt number. If it is always positive, then the system will be definitely unstable. Okay, yeah, I'll write that statement first. From the instant of disturbance occurrence, if always d delta by dt greater than 0, then system will be unstable. The d delta by dt was always greater than 0, then the system will be unstable. Okay. When we will say system is stable? Yeah, tell me please. When we will say the system is stable? Observe here. See, in case of stable swing curve, you can observe here. D delta by dt greater than 0 at the initial stage, means after the disturbance occurrence, greater than 0, greater than 0, greater than 0, greater than 0. And at one point, d delta by dt is 0. At one point, we are getting d delta by dt 0. I think this is a discrimination point between the stable system and unstable system. Between the stable system and unstable system, the discrimination point, the difference point is nothing but the d delta by dt equals to 0. See, in case of unstable swing curve, we are not getting the d delta by dt equals 0, but here the d delta by dt is coming 0. In the sense, from that view, what we should think is, okay, after reaching d delta by dt 0, it is expected that the angle may decrease from that point onwards, and it may exist in this manner, and we will say the system will be stable. System will be stable. All of you getting my point? Please tell me. All of you getting my point? Yeah. So I can say, from the instant of disturbance occurrence, disturbance occurrence, at any point, if d delta by dt equal to 0 occurs, if d delta by dt is equals to 0 occurs, then the swing curve, may come as in case 1. May come as in case 1, and the system is expected to be stable. System is expected to be stable. System is expected to be stable. Okay. Okay, yeah. So I'll tell you one more thing here. Kindly observe. In the stable swing curve only I am saying you. Just observe to me. Observe to this. See, strictly speaking, after reaching to this point, maybe after saying that the angle is becoming constant, then only we can confirm that the system will be stable. Strictly speaking, after reaching to this constant angle only, we have to confirm that the system is stable. But to reach that constant angle, we have to do that stability analysis for a long amount of time. For a long amount of time. So one more thing, what I am saying you is, you no need to tell me at what time it is becoming stable, at what time it is reaching to steady state, or at what time it is reaching to the stable steady state stable mode. That you no need to tell me. Just tell me what I am asking is, after the disturbance occurrence, transient, big disturbance occurrence, just tell me whether the system is having a capability to regain its stable mode or not. Whether the system is having a capability to regain its stable mode or not. That you tell, that is sufficient. In that sense, once after giving the disturbance, if you touch d delta by dt equals to 0 at one point, if you touch to d delta by dt equals 0 at one point, can we confirm that the system will be stable and angle will change more or less like this and finally reaches to some constant? Tell me please, have you understood my question what I said? Have you understood my question what I said? Just listen my question. Listen my question first. All of you, listen my question. Disturbance occurred. Angle is changing. D delta by dt I am calculating. It is positive. At one point I got d delta by dt 0. Can I stop? Listen. Can I stop? Stability study, calculation study at that point to say the system is expected to be stable. Yes or no? Can we stop at the point of d delta by dt equals 0 to confirm that the system is stable, and we can expect that we are going to get this type of power angle curve. I will tell you one more condition there, provided that there is no second disturbance in the system. Provided that there is no second disturbance in the system. Yeah. Yeah, nobody is syncing with this. I don't know what happened to you. Just listen concentratedly, Abhijit, Mubin. Just listen concentratedly what I am saying you. Listen concentratedly. It will become definitely stable. It will become definitely stable, provided that there is no second disturbance. Provided that there is no second disturbance in the system. I will explain once again. Leave all the things what you have in your mind out. Leave all the things whatever you have in your mind out. Just compare only the two curves what I have drawn here. Case 1 and case 2. Case 1 and case 2. In the case 2, it's an unstable system. Case 1, it's a stable system. Now the differences I am comparing between these two. In case of unstable system, I am observing that always d delta by dt is positive. But in case of stable system, for some time d delta by dt positive, and then it is reaching to 0, and then negative 0, positive 0, like that it is continuing, and then reaching to that stable mode, right? Reaching to that constant angle. What is it? Verge point, or what is it? What we call a concentrated difference here to decide whether the system is stable or unstable during the transient stability analysis means the point is d delta by dt equals to 0, which is not happening in case of the unstable system. Okay, so if after the disturbance has been occurred, if you touch d delta by dt equals to 0 at one point, then definitely it is expected that the system will be stable continuously. After that point onwards, you may get a different value of d delta by dt. Again, it will touch to 0 definitely. Again, d delta by dt may not be 0. Again, it will touch to 0. Again, may not be 0. Again, it will touch to 0. Like that, continuously, d delta by dt becomes 0 continuously, and finally, d delta by dt permanently becomes 0. Is it clear? Yeah, have you understood this, Ganesh? Have you understood this one, Ganesh, now? Yeah. Definitely. Second amplitude oscillation will be definitely less compared to that. See, some people are in a doubt, are in a feeling to ask a question, interested question, that, sir, why can't we have the delta versus time variation? Delta versus time variation, something like this. Why can't we have this like this? You don't have like this. You don't get this type of curve. You don't get this type of curve. Okay? As we are discussing about a undamped, damped system. Also, you can say under-damped system. We are discussing about a under-damped system. Definitely, it is expected that you don't get this type of curve. Either the angle will increase and then fall down and makes oscillations, finally reaches to constant angle, else angle will continue to increase. You don't get this type of curve. Yeah. I think all of you clear about this doubt. Yeah. So I think it's okay now. So let me proceed. Anyhow, I am saying you again, it is not the final point where we are discussing about this stability issue. Same comment we will be repeating in each and every case study further and further. Yeah, look here, look here. I am reading the statement once again. From the instant of the disturbance occurrence, at any point, if d delta by dt equals to 0 occurs, then the swing curve may come as in the case 1, as in the case 1, and the system is expected to be stable provided that there is no second disturbance. Provided that there is no second disturbance. Provided that there is no second disturbance in the system. Second disturbance in the system. Provided that there is no second disturbance in the system. Yeah. That may or may not be, Bharat. That may or may not be. As we move ahead, you come to know it. Sir, there is no continuous decrease of a curve. You don't get that type of curve. See, you don't get a swing curve, delta versus time curve. You may not get in our study. You may not get in our study something like this. Something like this you may not get. But you may get, it may oscillate. It may oscillate and finally it may reach to 0. Chance is there. Chance is there to say finally this angle may reach to 0. Chance will be there. Okay. But you don't get this type of curve. It is not expected, this type of curve. Okay. Yeah. Next. What do you mean by d delta by dt here? What do you mean by d delta by dt? What's the equation for d delta by dt we had derived? What we have derived about d delta by dt earlier? Tell me please. One equation we said in the discussion of swing equation itself, that is omega minus omega s. D delta by dt is equals to omega minus omega s. Means from the instant of the disturbance occurrence, omega value will vary. Omega value will vary and it won't be equals to synchronous speed definitely. It won't be equals to synchronous speed definitely. Because of that, we have the d delta by dt value either positive or negative and it is changing. But whenever the speed comes back to synchronous speed, then the d delta by dt will be 0 and the angle might have reached to the maximum value or might have reached to minimum value. From that point onwards, angle variation will be in the opposite direction. Angle variation will be the opposite direction. By that way also we can say the system is stable. Okay, I'll tell you this word. You tell me, is it correct or not? Tell me. From the instant of disturbance occurrence onwards, look all of it. From the instant of disturbance occurrence, at any point, from the instant of disturbance occurrence, speed of generator or speed of synchronous machine will change. Speed of synchronous machine will change. At any point, if that speed touches to synchronous speed, if at any point during the disturbance, if the speed touches to synchronous speed, then the system will be stable. Yes or no? Provided that there is no second disturbance. Provided that there is no second disturbance. Have you understood this one? Tell me, please. Yeah. See, after the disturbance has been occurred, if you don't touch to synchronous speed, then the system will be definitely unstable. Okay. So I will write the same comment inside this equation only. If d delta by dt is 0 or omega equals to omega s occurs, then the swing curve may come as in the case 1, and the system is expected to be stable. Then to know about this d delta by dt, is it 0 or non-zero? Listen all of you. I am saying one simple, of course, crucial point. To check whether this d delta by dt is 0 or non-zero, what you have to check now? What you have to measure? Anybody? What we have to measure? Omega? We have to measure omega, yes or no? Omega. But how to measure speed? Or how to calculate speed? Anybody? Is it possible to calculate speed value? No, we can't find the speed. Mathematically, I am saying, mathematically, how to calculate speed? See, that speed you have to get from the swing equation d omega by dt equals to pa by m. That speed you should get from the swing equation d omega by dt equals to pa by m, which is a non-linear differential equation. Which we can't integrate by direct integration. We have to follow numerical integration technique. Again, the method will turn into what? Numerical integration of swing equation. But you see, we derived one equation for d delta by dt just now. Right. See, this we can calculate easily. By hand calculation, we can do it. Square root of 2 by m. M is constant. Integral of PA d delta. What do you mean by that integral of PA d delta? What do you mean by this integral of PA d delta? Area under PA, accelerating power versus delta curve. PA versus delta curve area. Okay. So if d delta by dt is touching to 0 means this integral of PA d delta value will become 0. I'll write. Just listen. Another equation we have derived is d delta by dt equals to square root of 2 by m integral of PA d delta. We can say. D delta by dt equals to square root of 2 by m integral of PA d delta. So to get d delta by dt is equals to 0, I should say integral of PA d delta value must be equals to 0. Okay. Is it possible to find out this integral of PA d delta? So it is accelerating power versus delta curve. Area under PA versus delta curve. If that is zero, then what do you have to say? Listen kindly. Look at this reverse analysis. What you are doing now? First, what you have to calculate? Integral of PA d delta you have to calculate. After knowing about the integral of PA d delta, we are capable to know the value of d delta by dt. Clear? After knowing the d delta by dt, you can decide whether the system is stable or unstable. And how is the angle variation? Angle is increasing or decreasing. All these things you will come to know. But at any point, if the integral of PA d delta value comes to zero, then d delta by dt value will touch to 0. then we can confirm that the system will be stable, and case one swing curve may result in the analysis. So I think it's okay for you. I think it's okay. But area not equal to 0. Why Vinita? Why it will not be equal 0? Why Vinita? Why it will not be equal 0? Tell me. I'll tell you about that anonymous setting. Listen here. Listen. Means one simple comment what we can make here is to have this integral of PA d delta is equals to 0. In that integration duration, in some portion, PA value must be positive, which will create positive area. In the other portion, PA value must be negative. It will create a negative area. Then, if you have positive area as well as negative area, some of these two areas will come to be 0, expected to become to be 0. Then we can say that we touched d delta by dt equals 0 and the system will be stable. System will be stable. Okay, right. So I'll write to meet. I'll write here itself, I think. Yes. To get integral of PA d delta is equals to 0. To get integral of PA d delta equals to 0. In the integration duration, right, in in some portion of integration duration, some portion of integration duration, the PA value shall be positive. PA shall be positive, and in other portion of integration duration, PA shall be negative. PA shall be negative. Okay? Yeah. So try to understand this, what I said. Yeah, sorry, there is a network issue. Yeah, listen here. So, for your understanding now, I will be drawing that PA versus delta curve arbitrarily. Some curve I will show. In some portion, I will show positive, and some portion I will show negative, just for your understanding only. Right? It's accelerating power axis, and this is delta. Accelerating power axis, and this is delta. Okay. See, and this is your initial angle. Let me assume delta naught, and the accelerating power is changing with respect to angle, something like this. You assume like this, it is changing, and this is some angle I am showing delta 1, and this angle I am showing something like delta 2. Delta naught, delta naught, delta 1, delta 2. And you see this portion, whatever the area we have here, I will assume this area as A1. A1. Of course, in that portion, you observe that PA is positive. PA is positive. And in this portion, you observe that this PA is negative, and I will call this area as A2. How that A1 and A2 areas are looking to you? Whether these two areas are equal in magnitude, opposites in sign. Equal in magnitude as well as opposite in sign. So let us say that this A1 plus A2 is equals to 0. A1 plus A2 is equals to 0 in the sense integral PA d delta is equals to 0. Integral PA d delta is equals 0. Yeah, listen all of you. Listen all of you. This is one place where you get a doubt. This is one place where you get a doubt. Please listen concentratedly what I am saying. Integral of PA d delta equals 0. Okay. Is it a definite integral or indefinite integral now? It should be a definite integral, right? Over a range of delta, if you take the integration of PA versus delta, it should come 0, right? It should be a definite integral. Definite integral means what are the limits of delta now? Tell me please. What are the limits of delta? What are the limits of delta? Starting from delta naught to delta 2. Starting from delta naught to delta 2. All of you getting this one? Delta naught to delta 2. Integral PA d delta will be equals to 0. That we should say. I think all of you getting this. Delta naught to delta 2 integral of PA d delta will be equals to 0. Next thing. Look here. I'll write in the next slide. Don't confuse. Just listen. Next slide. Square root of 2 by m integral PA d delta. Okay, integral PA d delta. I am taking the limits as delta naught to delta 2. Delta naught to delta 2. That is equals to 0, right? Because at integral value of 0, so this square root of the term is 0. Square root of the term is 0. Please listen, Vaishnavi. Please listen here, Vaishnavi. 0. What is the meaning of this one? D delta by dt equals 0. The meaning of this is d delta by dt equals 0. At what angle? At what angle the d delta by dt is coming 0? Please be clear. What I am asking you. Integral delta naught to delta 2 PA d delta is equal 0. So square root of this term is equals to 0. Okay. This term is nothing but d delta by dt, right? This is nothing but d delta by dt. D delta by dt, at what angle you are doing the calculation? At what angle you are doing the calculation? Somebody is saying delta 1 also. Shyamala, up to what angle you have done the integration? Up to what angle you have done the integration? Dinesh, up to what angle you have done the integration? Up to delta 2. Up to delta 2 means this is the value of d delta by dt at an angle of delta 2, we should say. Clear? Dinesh, have you clear? Yeah, good, good. All of you understood this point? Simple, very simple. Up to what angle you take integration? Up to what angle you take integration? That square root of 2 by m integral of PA d delta will give you d delta by dt at that particular angle, that upper limit angle, delta 2. And this value is equals to 0 in the sense we touched omega is equals to omega s at an angle of delta 2, we should say. That implies omega equals to omega s occurs at delta 2 angle. Omega equals to omega s occurs at an angle of delta. Clear? Okay, next thing. Simple, very simple. I am calculating, for example, I am calculating square root of 2 by m integral PAD delta starting from delta naught to delta 1 only. Delta naught to delta 1. It is nothing but what? 2 by m integral delta naught to delta 1 PAD delta. What is that? What is that we should say? That is nothing but d delta by dt only, right? Listen, Abhijit, what I am saying. That is positive. That's okay. Positive only. It is non-zero also. It is nothing but d delta by dt only, right? At what angle? It is d delta by dt. At what angle? At what angle? Tell me. Delta 1. Okay. So this is at an angle of delta 1. And what is this value? It is not equals to 0. Not equals to 0. Next. Stop writing. Any other formula you have for d delta by dt? Any other formula you have for d delta by dt? What is that? Omega minus omega s. Omega minus omega s is another formula for d delta by dt. Omega s anyhow synchronous speed constant. What is omega? What is this omega you are talking now? It is omega at which angle? Tell me. Omega at which angle? Delta 1. Omega at the angle of delta 1. So this is one of the way of calculating speed at this given angle. If you want to calculate speed at a given angle, you take up that square root of 2 by m integral of starting angle delta naught to the angle where you want to measure the speed PAD delta. You calculate that number and that will make it equals to omega delta minus omega s. From that you will get the speed omega delta. Yes. Have you understood this? Clear? Yeah, okay. So this is a basic methodology of equilibrium criteria. So now we will look at what are the various delta 1 to delta 2 will be there or not. Tulsi, we are interested to calculate this integral only. We are interested to calculate only this integral. See, Tulsi, if you are taking from delta naught to delta 2, obviously delta naught to delta 1, delta 1 to delta 2 was covered, right? What's your doubt now? What's your doubt? If you take delta naught to delta naught to delta 2, obviously delta naught to delta 1, delta 1 to delta 2, both portions are covered. Yes. Simple mathematics. Yeah. Next. So next we are moving to different case studies on which we are going to study the transient stability of system. Different case studies on which transient stability analysis to be studied. This is our view. These are not the final case studies. These are not the final case studies. I'll say simply different case studies as a heading, sufficient. Different case studies. Okay, look here. First case study I'm saying. First case study. A sudden and large increment. Increment in mechanical input to the alternator connected to infinite bus. Okay, a sudden and large increment in the mechanical input to the alternator connected to infinite bus. Second one. Look here. A three-phase short circuit fault on a no load operating short transmission line very close to three-phase short circuit fault on a no load operating short transmission line at its sending end side. Right, connected to or very close to the bus bar, just after CV, just after the location of circuit breaker, I'll show that in a diagram. Kindly go through it. So this is one generator we have connected to one transmission line, and then we have some infinite bus bar. And I am showing that short line specially here, no load operating short transmission line. I'm showing breaker at this place, circuit breaker here, and I'm showing this as a fault location, very close to the bus bar, just after CV, very close to the circuit breaker, just after CV. Okay. So this is the fault location, what we are saying. I will explain about it. Don't bother. Just go through it, what I am saying. Yeah, next case study I am going to take up. That's a third case study. Third one. A three-phase short circuit fault. At midpoint of one of the lines in parallel line system. A three-phase short circuit fault at midpoint of one of the lines in the parallel line system. Right. So I'm showing here this is a SMIB single machine connected to infinite bus bar. See, all the case studies, what I am saying here is with respect to SMIB only. Single machine connected to infinite bus bar. It's a mechanical input TS, which is going to be maintained as constant. These are circuit breakers I am showing, kept on two sides of line, and this is a location of a short circuit fault. That's a third case. And then the fourth case study is a three-phase short circuit fault at the sending end side of one of the lines in the parallel transmission line just after the CV. A three-phase short circuit fault at sending end side of line, or a three-phase short circuit fault on one of the line in parallel line system, one of the line in parallel line system. Parallel line system very close to bus bar, very close to the bus bar, just after the location of the circuit breaker. Just after the location of circuit breaker. Three-phase short circuit fault on one of the line in the parallel line system. Parallel line system very close to the bus bar, just after the circuit breaker. Okay. So I will show the same diagram as it is. This one only I will repeat, but I will alter that fault location. I will change that fault location. Okay. So this is that parallel line system which I said just now, and this is not our fault location. This is not our fault location. Our fault location will be at this place, very close to the bus bar, just after circuit breaker. Very close to the bus bar, just after the circuit breaker. Okay, next thing. Next, fifth case study. Removal of one of the line in parallel line system. Parallel line system by opening circuit breakers intentionally without any short circuit fault. Without any fault. You keep this without any fault statement inside the bracket. This one inside the bracket. Removal of one of the line in the parallel line system by opening circuit breakers intentionally without any short circuit fault. Means I will show the system something like this. Okay. So for your understanding, I am showing this way. It's an infinite bus and it's a mechanical input PS. And this is a way how we are opening the breakers. The way how we are opening the breakers. So that one of the line was completely disconnected, the other line is in action. Other line is in action. Clear? Right. Next one. Next one we are going to say, sixth one. That is a sudden and large increment. Sixth one. A sudden and large increment in mechanical load on the shaft of synchronous motor. The shaft of synchronous motor connected to infinite bus bar. Connected to infinite bus bar. Connected to infinite bus bar. Right? So you can say like this. This is a motor and this is some mechanical load on the motor. And this mechanical load was suddenly added and it's high. Mechanical load was suddenly added and it is high. Yeah. Yeah. See. If you look at the 3 case studies, what I have given 1, 2, 3, 4 6 case studies total 6 case studies. See, first you tell me what are the different disturbances we can expect in the system. What are the different disturbances we can expect in the system? See, after all, I said in earlier classes also, either we have a disturbance on the input side of the system, or we have a disturbance on the output side of the system, or we have a disturbance on the network. Yes or no? Case number 1 is an input side disturbance, right? Case number 1 is the input side disturbance. Input, sudden and large increment in the mechanical input. Case number 6 is a load side disturbance, means output side disturbance. Whereas remaining 3, 4, 5, 2, 3, 4, 5 cases. 2, 3, 4, 5 cases are disturbance on the network. 2, 3, 4, 5 cases are disturbance on the network. Again, disturbance on the network is of 2 types. One is a fault. Next one, intentional removal of some element, contingency. Intentional removal of some element means contingency. Particularly case number 2, case number 3, case number 4 are dealing with fault. 2, 3, 4 are dealing with fault. Fifth case is a contingency study. Fifth case is a contingency study. Following all of you, almost all the types of disturbances what you have taken earlier have been inbuilt in these 6 case studies. In these 6 case studies. So I think all of you getting this one? All of you getting this? Yeah. Fine. Good. We have some announcements here regarding the class. Tomorrow, the class I will take from 6 o'clock evening. 6 p.m. to 9 p.m. is a class schedule tomorrow. And the day after tomorrow, that is tomorrow it's a Friday, right? Friday. And on Saturday, it will be from 2 p.m. to 9 p.m. 2 p.m. to 9 p.m. Of course, on Sunday also we have 2 p.m. to 9 p.m. Right? So we have some schedule adjustments. No, I am really sorry, anonymous attendee. We have some schedule adjustments. That's why. Please go through this. Tomorrow, 6 p.m. to 9 p.m. Saturday, we have some 2 to 9. And Sunday, 2 to 9. 2 to 9. Is it okay? Is it okay? Yeah. No. Saturday class we can't change. We can't change the Saturday class. Yeah, good. Okay. If you want, you can take tomorrow holiday. And then we have 2 to 9, Saturday and Sunday. Is it okay? No, it's not possible. Tomorrow holiday. Tomorrow I will give holiday. Then Saturday and Sunday will be like, okay? 2 p.m. to 9 p.m., 2 p.m. to 9 p.m. Yeah, fine. Good. Yeah. Thank you. And the dais is open for your doubts today. I made all the hands low. Please raise your hands if you have any doubt. Ramachandran, RA.
Yes, sir. Hello, sir. Hello, sir.
Your voice is not clear, Ramachandran. Please.
Sir. Hello, sir.
Tell me, Ramachandran.
Sir, in slide number 174, sir.
174, huh?
Yes, sir.
Okay. Tell me.
Sir, in this problem, the H1 and H2 are given, sir. For a system of, if it is not swinging, sir, why can't we use 1 by H1 plus 1 by H2, sir?
Where is that H1, H2 in this slide? 174.
Sir, I think in this, sir, first thing, sir. Yes.
Is this?
Yes, sir. Sir, no, sir. In 174 problem, sir.
174?
Yes, sir. In 174 problem, sir.
174.
Yes, sir. In 174 only, sir.
Are you looking the screen?
Yes, sir. Yes, sir. Yes,
Is
sir.
it
I'm
okay?
saying,
Do you
sir.
have any doubt?
So 1 second, sir. Sir, I'm sorry, sir. My doubt has been cleared, sir. I'm sorry, sir. I'm
Clear?
sorry, sir. I'm sorry, sir. Yes, sir.
Clear.
Yes, sir. Yes.
Okay, okay. Yeah. Dheeraj. Dheeraj. Tell me, Dheeraj, what's your doubt? Dheeraj. Are you there, Dheeraj? Okay. Tulasi.
Hello, sir. Sir, in 164F, sir. Hello.
160?
Four.
4.
First
Okay, what do you have?
Sir, that one I am not getting, sir. Why we are equating that?
So even though you are changing the base values,
Yes, sir.
kinetic energy will be remain same. That's the rule.
Okay. Kinetic energy.
Kinetic energy stored in the rotor
Okay, sir.
should be remain same, even though you are changing the base values.
Sir, base means ante voltage
G.
current change అవుతున్నట్టు
G,
కదా?
G. That is S base, S base.
Yes, sir.
That's the base, right?
Yes, sir. అంటే ఇప్పుడు ఫస్ట్ దాంట్లో 100 కింద దాంట్లో 150 ఉన్నప్పుడు వోల్టేజ్ కరెంట్ చేంజ్ అవుతాయి కదండి సార్ రెండిట్లో అప్పుడు.
Why you are bothering about voltage and currents? We are talking about energy and powers here.
Okay.
Getting me?
Yes, sir. Energy and powers.
Energy and powers we are talking here.
Okay, sir.
Yeah.
Okay, got it. Sir, 175. Sir.
175. Okay, tell me.
సార్ ఇక్కడ ఎలక్ట్రికల్ ఎందుకు తీసుకోలేదు సార్ మనము టీఏ?
Torque is a mechanical term, right?
Sir, 1 minute, sir.
Torque is a mechanical term, no?
Yes, sir.
So we have to take mechanical speed only here.
Yes, sir.
Should not take electrical.
Okay, sir. సార్ అది మెకానికల్ ఎప్పుడు తీసుకోవాలో ఎలక్ట్రికల్ ఎప్పుడు తీసుకోవాలో అని ఒక్కసారి ఎక్స్ప్లెయిన్ చేస్తారా సార్?
You tell me where you have doubt.
సార్ 186F సార్.
Good. Tell me.
సార్ ఇప్పుడు ఇక్కడ 180/F అది తీసుకున్నాం కానీ సార్
Why?
Sir?
What you want to calculate? For what purpose you are taking this one?
M =
Calculate? To calculate what?
1.
Tulasi,
Yes, sir.
you have written M equation GH/180F.
Yes, sir.
Why we are calculating M is to calculate some other quantity, right?
Yes, sir.
What is that other quantity you are interested to calculate?
We are calculating the delta.
Delta in which form?
In degrees.
Electrical degrees.
ఎలక్ట్రికల్ అంటే క్వశ్చన్ లో ఇవ్వడం వల్ల ఎలక్ట్రికల్ డిగ్రీస్ అనుకుంటున్నాం సార్.
Generally, delta rho triangle will be in electrical form only, right?
Okay, sir.
To maintain some uniformity between 4-pole, 2-pole machines and all.
Okay, sir.
It will be electrical degree.
Okay, sir.
That's why I am taking M in electrical degree here.
Yes, sir.
Tell me.
Okay, now got it, sir. I understood now, sir. And result ని బట్టి పైన M తీసుకోవాలో మనము RPM.
According to your requirement, what you want to calculate finally with that M.
Okay, sir.
That will decide in what units we should keep it.
Okay, RPM చేసినప్పుడు మెకానికల్ తీసుకోవాలి.
Mechanical radians we take.
Okay. మెకానికల్ రేడియన్స్ అని ఎందుకు చెప్తున్నాం సార్ అక్కడ మళ్ళీ?
You need to have that rotations per minute RPM, right?
Yes, sir.
So that's the reason we'll go with radian there.
Okay, okay, sir.
Yeah.
Sir, ఇంకొక 181F లో లాసెస్ తీసుకోమా సార్ మనము అక్కడ?
It's a lossless system, right?
Okay, resistance.
See, in the examination, Tulasi,
Okay,
we
sir.
didn't mention whether the system is having a loss or lossless.
Okay,
We have
sir.
to assume it as lossless only.
Okay, sir.
Okay?
Okay, sir.
Yeah.
మామూలుగా ఇప్పుడు న్యూమరికల్ తో చేస్తామన్నప్పుడు ఆ గ్రాఫ్ ఏమన్నా గీస్తామా సార్ మనం ఎప్పుడన్నా డెల్టా వర్సెస్ టీ కి?
Okay, if you proceed further to the case studies and all, you will show the graphs.
ఓకే. మనం చూపించేది ఈక్వల్ ఏరియా క్రైటీరియా గ్రాఫ్స్ కదండి సార్.
Which one? Power angle curves.
192 ఎస్ డౌట్ నాకున్నది.
192,
ఎస్ సార్.
Okay.
న్యూమరికల్ ఇంటిగ్రేషన్ ఆఫ్ స్వింగ్ ఈక్వేషన్ చెప్పాం కదండి సార్ ఇక్కడ.
Here we can draw the delta versus time and we will decide whether the system is stable or unstable based on that.
ఓకే. అది ఎలా?
But listen.
Okay.
How means we have to solve the swing equation, right?
ఎస్ సార్.
But in second method, so-called equal area criteria, we can't draw that curve. Delta versus time, we can't draw.
ఓకే సార్.
But you can draw for your understanding, right?
ఎస్ సార్.
With numbers, maybe you know angle numbers, but you don't know timings.
ఎస్ సార్.
But still, you can expect how might be the swing curve.
ఎస్ సార్. ఆఫ్టర్ సమ్ కాన్స్టెంట్.
Yes.
అదే అలాంటి గ్రాఫ్స్ ఫస్ట్ దాంట్లో నాకు అంటే మనం ఎక్కడ గీయలేదు కదండి సార్ ఆ గ్రాఫ్స్.
See, actually, Tulsi, in
ఎస్
the
సార్.
first case, you are capable to know what is the delta value for each and every timing,
ఎస్ సార్.
so that you can write.
ఎస్ సార్.
But in case of equal area criteria, you know only angles. What is the upper angle, bottom angle, middle angle,
ఎస్ సార్.
but you don't know timings.
ఎస్ సార్.
So, as you know, upper angle means maximum angle, minimum angle, middle angle.
ఓకే.
I will draw it by hand. It may be like this,
ఓకే. విత్ నాట్
irrespective of timings. Irrespective of timings.
ఓకే సార్.
So, as you don't know time, it's not an exact curve, right?
ఎస్ సార్.
So, we will say I can draw an approximate or expected swing curve,
ఎస్ సార్.
which may not be accurate one.
ఓకే. ఓకే.
Okay.
గాట్ ఇట్.
Okay. As we proceed to the case studies, you will come to know the things.
ఓకే సార్. 194 ఎఫ్ సార్.
Okay.
సార్ ఇక్కడ ఇవి చెప్పారు, సెన్సార్స్ చెప్పారు కదండి సార్, 4th పాయింట్.
Yes.
ఇప్పుడు ఫస్ట్ అక్కడ ఫాల్ట్ జరిగిన తర్వాత ఇప్పుడు 0 అయిపోయి ఉంటుంది కదండి సార్ మన వోల్టేజ్.
Okay.
అది సెన్స్ చేస్తారు సార్, సెన్సార్ 0 వోల్టేజ్ వచ్చిందని చెప్పి. మరి ఆటోమేటిక్ వోల్టేజ్ రెగ్యులేటర్ ఏం పంపిస్తుంది సార్ అక్కడ ఇన్పుట్ కి?
It will control excitation. DC input voltage you have na for rotor field winding. You have DC input voltage, right?
ఎస్ సార్.
That will be controlled by the automatic voltage regulator.
అంటే ఎంత వరకు కంట్రోల్, అది లిమిట్ ఏమన్నా ఉంటుందా సార్ ఇక్కడ? ఇంతరా
ఎక్కడ?
ఇప్పుడు అవుట్పుట్ వోల్టేజ్ 0 రావడం కోసము ఇన్పుట్ కూడా మనకు 0నే ఉండాలి, జనరల్ గా అట్లా తీసుకుంటాం కదండి సార్.
Output voltage to be 0.
ఎస్ సార్.
Ah.
ఇన్పుట్ లో కూడా వోల్టేజ్ 0 ఉండాలి కానీ సార్, లేదంటే ఇప్పుడు ఇన్పుట్ లో ఇస్తే అవుట్పుట్ లో 0 ఉంది, అది ఈక్వల్ అవ్వదు కదండి సార్.
That you should take with respect to energy. You see, you draw equivalent circuit of generator, you come to know. Just you keep one voltage source in series with impedance.
ఓకే సార్.
And terminal short circuit means terminal voltage is 0.
ఎస్ సార్.
Then where that voltage source has gone, that was appearing across the impedance, right?
ఎస్ సార్. ఎస్ సార్.
That's it. What's the doubt you have in that?
నాకు వచ్చేసి ఇప్పుడు ఆటోమేటిక్ వోల్టేజ్ రెగ్యులేటర్ ఎంత వోల్టేజ్ దానికి సప్లై చేస్తుంది అని డౌట్ వస్తుంది.
It will attempt to make the terminal voltage as rated value.
ఓకే సార్.
But it will have its own limitation, right? AVR will have its own limitation, na?
ఎస్ సార్.
Understanding what I say?
నో సార్, లిమిటేషన్.
Automatic voltage regulator cannot control. For example, voltage is fallen down to 0 at that case. It can't rise up that voltage value starting from 0 to the rated value by controlling the excitation. There are some limits on excitation.
ఓకే సార్.
Up to that limit only, it is capable to control that value. Beyond that limit, it can't.
ఎస్ సార్.
Yeah.
దట్స్ వై ఓన్లీ వి ఆర్ టేకింగ్.
Understood now.
ఇంకొంచెం క్లారిటీ రావడం లేదు సార్. నా డౌట్
Okay.
ఏమిటంటే ఆటోమేటిక్ వోల్టేజ్ రెగ్యులేటర్ మరీ వోల్టేజ్ అదే పంపిస్తుంది అని చెప్తున్నాం కదండి సార్.
No. Look here. See, for example,
ఓకే సార్.
this is the excitation provided for the rotor field winding
ఓకే.
by means of DC voltage source, in the sense DC shunt generator.
ఎస్ సార్.
Okay, and it's connected in this manner. See, whatever the field current you say IF, it will have its own limits, right?
ఎస్ సార్.
There is a minimum field current as well as maximum field current. Between those two values only, you are capable to control it.
ఎస్ సార్.
In the similar way, there will be some limits on the induced EMF also, right?
Yes, sir.
We have some minimum induced EMF and maximum induced EMF. Between those two values only we are capable to control it.
Yes, sir.
Understanding?
Yes, sir.
Yeah. So in that case, even though your terminal voltage is 0, and the voltage sensor has sensed that voltage as 0, that's okay.
Yes, sir.
And it has given a command for automatic voltage regulator. Automatic voltage regulator is sensing that voltage is 0. Then
Yes, sir.
it will try to give a command for this excitation system, and it will try to maintain this E value at maximum value.
Maximum.
That's it. Only up to that level it can go. It can't go beyond that, right?
Yes, sir. ఎందుకు maximum కి వెళ్తది సార్ అది?
Because this is 0 already. Terminal voltage.
Okay, sir.
Terminal voltage is 0. See, by controlling this key, what it is attempting to do, it is attempting to control terminal voltage only, right?
Yes, sir.
So even though it is attempting to increase the excitation, terminal voltage must remain 0.
Yes, sir.
Then still the automatic voltage regulator will say that the terminal voltage has not reached to its rated value. Please increase the excitation.
Yes, sir.
It's increasing excitation. Again, the terminal voltage is still 0. Again, AVR will say that the terminal voltage is still low value. Please increase the excitation.
Yes, sir.
Beyond certain value, the excitation will not go high.
Yes, sir.
So excitation will settle down to maximum then.
Maximum. Okay.
Beyond that, it can't increase.
Okay. After some time, it will also become constant.
Yes.
Okay. But some middle process ni manam neglect chestunnama
Yes.
sir.
That variation we are neglecting.
Now got it.
Other way of saying this is, for example, fault is not at the terminal.
Yes, sir.
Maybe at some far location we have. At far location we have the fault.
Yes, sir.
Then whatever the terminal voltage you have here, mod VT. For example, you assume it's a 11 kV rated machine.
Okay, sir.
And this VT may be, let us say, 7 kV.
Yes, sir.
How much jump is needed? 5 kV. 4 kV jump is needed.
Yes, sir.
Then this AVR will identify the terminal voltage 7 kV.
Yes, sir.
Which is less than 11 kV.
Yes, sir.
It will give a command for excitation control.
Yes.
Field current will increase. Excitation EMF will increase. Okay?
Yes, sir.
Because of this increment, this terminal voltage will go up 8 kV, let us say.
Yes, sir.
After observing this as 8 kV, again AVR will say that still your terminal voltage is low. Please increase the excitation.
Yes, sir.
And this E value will increase, and it may go, let's say, 10.5 kV.
Okay, sir.
Then again this AVR, what it will say?
Increase. It is not
Increase the excitation.
Yes, sir.
If it is unable to increase the excitation beyond that value, it will settle down to maximum.
Yes, sir.
If it is capable to increase the excitation, it can increase, and this voltage may go to 11 kV.
11 kV. ఆ ఫాల్ట్ జరిగినది దీనికి ఏమి రిలేషన్ ఉండదా సార్ లాంగ్ లైన్ లో ఇక్కడ ఫాల్ట్ జరిగింది అని అన్నాం కదండి సార్ మనం అదేమి ఈ టెర్మినల్ వోల్టేజ్ కి దానికి రిలేషన్ ఉండదా సార్?
Definitely we have some current flow in the system, right?
Yes, sir.
Because of heavy current flow only, this terminal voltage is falling down, right?
Yes, sir.
That is going to be corrected by the AVR mechanism.
Yes, sir.
If it is doing that, it is controlling this induced EMF value.
Yes, sir.
If you are controlling that induced EMF value, your Pmax value will be variable with respect to time.
Yes, sir.
Delta also variable with respect to time. But your aim is to study delta versus time. That's why we are assuming that E is constant.
Okay, sir. Yes, sir. No, got it, sir.
Clear?
Yes, sir. Sir, saliency in alternator source neglected. That once, sir,
XD, XQ difference we have, right?
Yes, sir.
That we are neglecting. In the sense, strictly speaking, if you have salient pole machine, we have to consider the direct axis reactance as well as quadrature axis reactance into analysis.
Yes, sir.
Okay? But if you are taking the two reactions, means two reactances into the analysis,
okay, sir,
handling the problem is a bit difficult.
Okay, sir.
That's why we are assuming that XD and XQ values are equal.
Yes, sir.
So that we don't have any reluctance.
Yes, sir.
Reluctance variation we don't have.
Okay.
So that will be taken simple as a round robin alternator, and we can proceed with the study.
Okay, sir.
Okay.
Okay.
Sir,
నేను అక్కడ అడిగినది డెల్టా 1 డెల్టా 2 అంటే లోయర్ లిమిట్ డెల్టా 1 అప్పర్ లిమిట్ డెల్టా 2 తీసుకోకూడదా అని అడిగాను సార్ అప్పుడు నేను.
No, you should not start from delta naught only, because from that point only you have that area started, right?
Yes, sir.
Before that you don't have area. You have to start from delta naught only, to find out speed at any angle further.
ఓకే సార్. అక్కడ అప్పర్ లిమిట్ ఏది ఉంటుందో అక్కడ మనం స్పీడ్ క్యాలిక్యులేట్ చేస్తామా
Yes.
సార్?
No, it will come.
ఎస్ సార్.
If you take integration up to the upper limit,
Ah.
it will give d delta by dt at that angle.
ఓకే సార్.
So obviously it will give speed at that point.
ఓకే సార్.
Okay.
థ్యాంక్ యూ సార్.
Meena.
సార్
Tell me, Meena.
సార్ ఇక్కడ స్పీడ్ గవర్నర్ చూడండి సార్, అది ఎక్కువసారి ఎక్స్ప్లెయిన్ చేస్తారా సార్?
Yes. See, whenever you have that speed governor, particularly during short circuit fault, electrical power output will fall down. Na?
ఎస్ సార్.
During short circuit fault, electrical power output is falling down. And we have PS minus PE positive.
ఎస్ సార్.
Then what will happen to d omega by dt? Positive.
ఎస్ సార్.
PS minus PE is d omega by dt, right? PS is there, but PE is 0, so d omega by dt is positive. Means what will happen to speed of this machine?
ఇంక్రీజెస్.
Increases, right? Whenever speed is increasing, what will happen to frequency of operation?
ఫ్రీక్వెన్సీ ఆల్సో ఇంక్రీజెస్.
Increases. Then the frequency sensor is sensing that the system is operating at higher frequency. Okay.
సార్.
Then whenever it is operating at higher frequency, it will give a command for speed governor mechanism in order to control the PS value.
ఇన్ ఆర్డర్ టు కంట్రోల్ సార్?
PS, mechanical input.
ఓకే సార్.
Okay. Then what it will try to do? It will try to reduce the mechanical input. Actually, always the speed governor will try to match electrical output and mechanical inputs.
ఓకే సార్.
By controlling the mechanical input, it will try to match that value to be equals to electrical output value.
ఓకే సార్.
If it is doing that, obviously PSC is varying with respect to time.
ఎస్ సార్.
So that variance I am not allowing because it will create more difficulty in the analysis. So that we are assuming that speed governor mechanism was deactivated.
ఓకే సార్.
Okay.
థ్యాంక్ యూ సార్.
Yeah. Yogesh.
Hello, sir.
Tell me, Yogesh.
Yes, good evening, sir.
Good evening.
Sir, actually, how to represent three winding transformers are in sequence network?
Winding transformer in sequence. So you can draw simply like this. It's a primary, secondary, tertiary. Okay.
Yes,
ZP
okay.
per unit, ZS per unit, ZT per unit.
Yes.
And simply you keep the series switches and shunt switches. It's a series switch on primary. Shunt switch on primary. Operated according to the connection delta star.
Sir, and in positive and negative directly combine, sir.
Combine, that's it.
Okay, sir. Sir, that means secondary two will come in direct parallel and in series with that.
No, just
Positive.
look this diagram. Are you clear about this diagram now?
Yes, sir. Actually, I am clear about the zero sequence because I saw one problem in according to that. But
Okay.
in positive and negative sequence, I was.
Positive sequence and negative sequence, it will be simply like this only. Like this, that's it.
Okay, sir. Sir, and in one problem I had a doubt, sir. Sir, they have asked to calculate the fault current on phase A. One LG fault is given, sir. They have asked to calculate fault current on phase A. Then we
Okay.
take 3 by Z1 equivalent plus Z2 equivalent plus Z0 equivalent, na, sir.
Yeah.
Sir, in solution they have taken 1, sir, in numerator, sir, actually.
They might be calculating only positive sequence current.
Sir, in question they have given to calculate fault current on phase A.
Then you, whatever the procedure you are following, that is correct. Leave that solution aside.
Yes, okay, sir. Okay, sir. And other doubt I had, sir. Sir, in LLG fault, sir. Sir, we take that numerator. We take that pre-fault voltage, no, sir. Sir, that we take line to line voltage or phase voltage, sir.
You are trying per
voltage.
phase network, right?
Yes, yes, sir.
It's a per phase voltage.
Okay, sir. Okay. Thank you, sir. That was
Yeah. Gopi Raju.
Yes, sir.
Tell me, Gopi Raju.
Yes, sir. Please open 196th page slide.
Okay.
Here discussed about frequency sensor as well as a voltage sensor. Here at the sending and bus bar, here we are taking only single generator. The entire explanation I understood, but if we can place more than 3 or 4 generators in parallel to the existing generator, whenever there is a fault occurring in between transmission line, how can we say that which generator sends the frequency or voltage sensor? How can
for each generator we have their own speed sensor and frequency sensor and voltage sensor.
That's that point I understood, but in this transmission line only one frequency sensor, only voltage sensor. These sensors, which generators it can sense that signal. All the generators.
Where you are keeping the sensor? Is it on transmission line or at the generator location?
Transmission line, sir.
Generator location you will keep, right?
Generator location, sir.
These are control loops of generator.
Okay.
AGC loop and AVR loop.
Okay. Each individual
control loops of generator unit.
Okay, but how if the fault happens at transmission line, how can we sense that frequency as well as voltage sensor?
What will happen after the fault occurred?
The speed will changes, automatically voltage changes, the reactive power drawn by the fault will increases.
Speed changes means frequency will change.
Yes, sir. My point is that which generator has to be
all generators will see. All generator speeds will change, right?
All generators is changes, sir.
Definitely.
If any one of the generators has maintained the speed before as well after the fault, then there is an mishap happens, and that's what my small doubt.
Nothing. See, for at every generator, you have a speed governor as well as automatic voltage regulator.
Yes, sir.
Any fault occurred on the system, definitely electrical power supplied by each and every generator will change.
Okay.
According to that, each and every generator will have its own acceleration.
Okay.
Then the frequency sensor, if it is sensing, obviously for each and every generator, there is a control of the steam input.
Okay. That's my doubts. Sir,
is it clear now?
Yes, sir, clear, sir. Sir, last, I think it's last pages, sir.
Tell me.
Various faults happening in a system, double circuit middle of the transmission line and the starting point of the transmission line. Even though most of the three-phase fault occurrence in a system is probability is very less, why can't we discuss LG faults? Why we discuss only triple L faults or triple LG faults?
Which is more severe fault?
Severe fault is triple L or triple LG fault.
Okay. See, if the system is stable for three-phase, listen.
Yes, sir.
If the system is stable for three-phase fault,
okay,
can we say it is stable for LG?
Yes, sir.
That's it.
That's the only.
We are doing worst analysis here.
Okay.
What fault is most severe one? You do the analysis based on that.
Okay.
And you maintain your conditions in such a way that the system is stable for that type of fault.
Okay.
Then system will be stable for remaining faults also, right?
Okay, sir.
Understood?
Sir, yes, sir. Understood. So, circuit breakers as well as sensors may know which fault it is based on the fault current. It will decide whether it is a triple L fault, LG fault. Is that correct, sir?
Breaker will not decide it actually. Relay will sense.
Relay, sir. Sorry.
Even though the relay is sensing that, it will give a command for opening of all the 3 lines.
Okay, okay,
For example, if it's a 3-phase line ABC wires,
okay.
for example, if you have a single line to ground fault,
Yes, sir.
but still all the 3 lines will be opened up.
Yes, sir.
If it's a LL fault, all the 3 lines will be opened up.
Okay.
Irrespective of type of fault,
Hmm.
the complete 3-phase circuit is going to be disconnected
Okay, okay,
by the breaker.
okay, okay. After that, sir. After that, how
After that,
fault will clearing? Then all 3 phases are so
who
open.
will clear the fault?
Who will clear?
We have to
Practically.
go along the line.
No, sir. Yes, sir.
Yes, Gopiraju. How
Using
fault
the
will be
software,
cleared?
it will.
It won't clear on its own,
It
right?
will know. No, sir. It will know the location.
Listen. After the relay was sensing the fault, it will
Okay.
give a command for breaker to open.
Yes, sir.
Breaker will open.
Okay.
Practically, we have a kind of reclosed type breakers.
Okay.
Reclosed type breakers means after the relay gives signal to it, it will open, but after a definite amount of time, it will close again.
Okay.
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 For example, first relay sensed the fault.
Okay.
It is given a command for breaker to open.
Okay.
Breaker was opened.
Okay.
It is waited for some time in that way only, opening only.
Okay.
Then closed.
Okay.
After closing it, in between that time, between that opening and closing, there is a time gap, right?
Okay.
Within the time gap, if the fault was cleared,
Yes.
then it will be permanently closed
Permanently closed.
because relay will not sense that as a fault further.
Okay. Okay.
If the fault was not cleared permanently, then once after closing the breaker, relay will sense that still there is a fault on the system.
Okay.
And it will give again a command for breaker to open.
Okay.
And breaker will open. Maybe it will be a permanent open from that point.
Okay. Okay.
So that is the identification of permanent fault on the system.
Okay. Okay.
Okay. Once after opening the breaker,
Okay.
and the substation men, what we have, they finalized that we have a permanent fault on the system. We have to identify where it has happened.
Okay. Okay.
According to the data provided by the relay,
Okay. Okay.
means how much current, at what current it was cleared the fault.
Okay. Okay.
Okay, based on those numbers,
Okay. Okay.
they will try to go with a raw assumption that
Okay.
at which location the fault has occurred from the location of substation.
Okay. Okay.
Means at how much length the fault might be occurring.
Okay. Okay.
Okay, they will take some zone. Let us say they expected that the fault is occurring in between 10 kilometers to 15 kilometers gap.
Okay.
Okay, we have a 5 kilometers distance of line.
Okay. Okay.
Along that 5 kilometers length of line, they have to walk.
Okay. Okay.
They have to walk and check continuously that line where the fault was occurred.
Okay. Okay.
After they have identified it, they have to rectify it and inform to the substation, close the breaker.
Okay. Okay.
Okay.
Okay, sir. Sir, can you open an 193 page slide?
Okay.
193. Yes, equilibrium criteria based. Yes, sir. Sir, here only single generator connected to the bus bar, equilibrium criteria applicable, as well as there are so many 2 or 3 generators are connected to the bus bar. It will converted into equivalent. Then we can apply equilibrium criteria. Yes, sir.
Yes. Yes.
So my question is it applicable for both incoherence or non-coherence? Both can be applicable, or
Whether the 2 machines are in coherence or not in coherence, you can convert into single machine, right?
single machine? No, okay, sir.
Then it can be applicable.
That's my doubt. My doubt is only in incoherence or non-coherence.
No. Non-coherence also, 2 machines in not in coherence. You can
Whatever it may
convert
be, if you are able to convert into equivalent single system, then we can apply equivalent criteria.
Yes.
Okay, sir. Thank you, sir.
That's it, Gopi. Okay.
Yes, sir. Thank you.
Nikita.
I have doubt in one question, sir.
Tell me.
They given one phasor diagram, one network, sir. 4 points on that. They
Okay,
given one phasor.
Have you gone through the solution?
No, sir. I didn't understand that, sir.
Have you gone through the solution?
No, sir.
Please go through the solution once.
Okay, sir.
Okay.
Okay.
I've written some reasons why the fault has been occurred at certain location. Why can't it be in the other location? Okay.
No, sir. They given that question is to find the fault, sir. Where there is fault point, sir.
That's what I am saying, you Likita. You please go through the solution what I have provided in the book
Okay, sir.
first.
Okay, sir.
Okay. After going through the solution, if you have any
Okay.
if you have any doubt, you can ask me.
Okay, sir.
Which book you are saying? Workbook or previous gate questions?
Previous gate question.
Previous gate questions means solution is available. Yes or no?
Yes, sir.
Go through the solution first. Which book you are following? Our book only, right? Yes.
Yes, sir.
Yes, 2021, 22 book. Gate book.
Yes, 2020.
Okay. Go through the solution. Try to understand it first.
Okay.
Yeah.
Okay, sir.
Okay. Sai Charan Reddy.
Hello, sir.
Tell me, Sai Charan.
Sir, I lost. Sir, after some time I lost.
Nobody is there today.
Okay, okay, sir.
Okay, Bhaskar. Bhaskar.
హలో
Tell me, Bhaskar.
హలో సార్, ఇది సింక్రోనైజింగ్ పవర్ అంటే మాక్సిమం చేంజ్ అంటే ఫాల్ట్ అక్కర్ అయినప్పుడు మాక్సిమం చేంజ్ ఈజ్ యాక్సెప్టబుల్ బై ద జనరేటర్.
No.
మరి ఏమని అంటాం సార్ ఇది సింక్రోనైజింగ్ పవర్ మీన్స్?
Synchronizing power means that is a change in the power delivered by the alternator for small disturbances.
ఓకే సార్.
Okay.
సింక్రోనైజింగ్ పవర్ కోఎఫిషియంట్ మీన్స్
dp by d delta. dp by d delta is synchronizing power coefficient.
Yes, sir.
Delta p is a synchronizing power.
Okay, okay, sir.
Those two terms are confined to only small disturbances or for steady state stability. That's it.
Okay, sir.
In the transient stability, you should not call those terms during transient.
ఓకే సార్. సార్, మనం ఇండక్షన్ మోటార్కి ఈ రోటర్ యాంగిల్ ఇష్యూ అనేది ప్రాబ్లం అనేది ఎగ్జిస్ట్ కాదని చెప్పారు కదా సార్?
Yes.
ఎందుకు సార్ అక్కడ?
You don't have induced EMF, right?
అంటే బ్యాక్ ఈఎంఎఫ్ ఉంటది కదా సార్?
Where you have back EMF?
ఓకే, ఓకే.
You are not providing any excitation.
ఓకే సార్.
And you are not causing for any induced EMF in stator.
ఓకే సార్.
Okay.
ఓకే సార్. సార్,
Tell me, Bhaskar.
సార్, ఇది రిలేస్ సర్క్యూట్ బ్రేకర్స్ అన్ని మనకు సబ్ స్టేషన్ లో ఉంటాయి కదా సార్?
Yes.
అప్పుడు ఇవి అంటే ఎట్లా అంటే రిలేస్ ఎట్లా సెన్స్ చేస్తుంది సార్? అంటే వైర్ ఏమైనా ఎగ్జిస్ట్ అవుతుంది సార్ బయట ట్రాన్స్మిషన్ లైన్?
మీకు అక్కడ కరెంట్ ట్రాన్స్ఫార్మర్స్ పెడతారు కదా, సిటీపీటీ.
ఓకే సార్.
ఆన్ ద లైన్స్.
అంటే వాటికి కనెక్షన్ త్రూ అంటే అక్కడ నుంచి మనకు
పవర్ లైన్. డెఫినెట్లీ ఇట్ విల్ బి కనెక్టెడ్ టు పవర్ లైన్.
ఓన్లీ అంటే సిటీపీటీ కనెక్షన్ లైన్ కి ఒక సెపరేట్ వైర్స్ ఉంటాయా సార్?
Yes.
ఓకే, ఓకే సార్. ఓకే, థ్యాంక్ యూ సార్.
That's it, Bhaskar?
Yes, sir.
Okay. Imtiaz.
Good evening, sir.
Good evening. Tell me, Imtiaz.
Sir, in last topic, different cases studies kana before one. You said no square root of 2 by m. Sir, if we take delta naught to any other than delta 1, at the time the speed will be at delta 2.
At that point, you'll get speed. That's it.
Sir, omega means the rotor speed, no sir. Generator rotor speed.
Rotor speed. Yes, yes.
Where omega s is the reference is
Constant. Reference speed, infinite bus speed.
Okay. If we take delta naught to any delta 3 means we are measuring the
You'll get
delta
speed
3
at that
speed.
other angle, other upper limit angle, what you have considered.
Okay, sir. Sir, in the formula you said no sir, one is the always for PE constant we are taking that formula.
PE constant.
Sir, for the acceleration power, sir.
Okay. Delta speed.
Sir, if the acceleration power is not constant at that time, any formula is there?
No, we don't have that formula. You have to go for solution of swing equation only.
Based on the swing equation.
That's it.
Sir, one more. Sir, in case one, case 2, there is two waveform, no sir. Sir, you said no. The upper limit will be never goes to more than that value. Because of that, we are considering only one disturbance, sir.
Only one disturbance. Yes.
If you take more than 2-3 reasons, we will go up and down.
No. It will go up the continuous increment. It may happen. For example, first disturbance occurred.
Okay.
We met d delta by dt 0. Angles start decreased. But after decreasing the angle or in that decreasing mode, another disturbance came.
Okay.
Then again angle may oscillate and finally reaches to some value, one chance. Other chances it will continue to increase.
Okay, sir.
Okay?
Yes, sir. Sir,
you don't get rising oscillation.
Sir, it may be possible, no, sir, if you take more than 2-3 disturbance at a time.
At a time, even though you take more than 2 or 3 disturbances, it will continue to increase. That's it, right?
On second case, unstable case.
Unstable case, you are going to.
Okay, sir. Sir, I sent that problem, sir.
Which one?
There is a each has reactance to positive sequence current of 5%. I'm not question that.
Read that problem once.
Okay. 6,600 volts, 10 MVA, 3-phase alternators are connected to a common set of bus bars. Each has reactance to positive sequence current of 5%. Their reactance to negative. Their reactance to negative and zero sequence current are 75% of 30% of the positive sequence value.
Okay, what is there in that x1 value? You take 0.05.
But I take, sir, but in the solution
x2 how much? x2
75% of the 0.05.
Means 0.75 into 0.05.
Yes, sir.
x0 0.3 times of 0.05.
Yes, sir.
Okay.
But in the x1 is equal to 0.6534.
0.653.
Yes, sir.
You convert into ohms?
Yes, sir.
Okay. Then okay, what's your doubt there, Imtiaz, in that?
Sir, its value is wrong.
Which value wrong?
The positive sequence current is 5%, sir.
Okay.
5% means per unit value. We have for getting the actual value into a base, no, sir.
Okay, that you can do. What is there? What's the doubt you have in that now?
The answer is not matching, sir.
What they have asked you to find ultimately?
Calculate the magnitude of the fault current. That's all, sir.
Which fault?
LG fault, sir.
Okay. What they have taken in the solution?
they are taking some calculations, sir.
X1 value, how much they have taken?
0.6534 ohm.
Have you converted your X1 value into ohms?
Yes, sir. I converted. I am getting the.
Are you getting
19
same?
No, sir. I am not getting same.
Okay. What is your jet base?
6.6 kV by root 3.
Jet base is how much? What is the V base value?
V base is 6.6 kV.
6.6 kV line to line.
Yes, sir.
Okay. What is the S base?
10 MVA.
Calculate jet base now. 6.6 square by 10. How much?
$4.356.
Ohms, huh?
Yes, sir.
Total.
Yes, sir.
4.346 ohms.
Yes, sir.
Then what is X1? 0.05
Yes,
multiplied with 4.346. How much?
Sir. 0.22, sir.
This is a ohmic value.
Yes, but in this there is a question. Answer is a 0.6534, sir.
Can you cross check the base values once again? Read the problem from beginning.
6,600 volt, 10 MVA, 3-phase alternator are connected to common set of bus bars. Each has reactance to positive sequence current of 5%.
Okay.
The reactance to negative and zero sequence current are 75% and 30% of the positive sequence value.
Okay.
And at the fault occur on the one bus bar. Calculate the magnitude of fault current if all the alternators are neutral or solidly electric.
X1 value 0.22 ohms only.
But in answer is 0.653.
Then that answer is wrong there.
Sir, okay, I consider this wrong. But in this question said that each has reactance to positive sequence current of 5%, sir. Any change meaning?
Nothing, no change.
I
With what
sent
they
that
have
answer.
started the solution?
Fault current in the amps,
First
sir.
they have to convert the values, right? Have you sent
Yes,
me
sir.
the solution?
Yes, sir, I sent, sir.
Yeah. Sent now in Telegram?
Yes, sir. Just I sent, sir. 1 second.
Where is it? You didn't send me.
Sir, I sent, sir.
Positive sequence current of 5%.
Yes, sir.
Each has a reactance to positive sequence current of 5%. I don't think so. It will be 0.05 only, I think, per unit.
0.05.
Yes, it will be 0.05 only.
Means that
It will offer a
solution is wrong.
reactance of 5% for positive sequence current.
Yes, sir.
Okay?
Yes, sir. Means x1 equal to 0.05, sir.
0.05 only, I think.
But the answer in solution, sir. In solution, they are.
They have done
giving
something. They have calculated current and they calculated. 1 minute, please. Ultimately, they calculated a jet base only. They have taken 15% here in the answer. In the solution, they have taken 15%.
Sir, at that time, the answer will be 0.06 0.65, sir. If you take
Ah,
15%.
they have taken wrong calculation in the answer. They have taken 15% in the answer. X1 value, they have taken
Okay.
15%. Have you seen that step? X into
Okay.
875 by 6600 by root 3 equals to 15 by 100.
Yes, sir.
They have taken 15 there, right?
Yes, sir.
15% they have taken in the solution, but in the question, how much they have given? 5%.
5%.
If you calculate with the 0.15, for example, you take this one 0.15, you will get this number 0.6534.
Yes, sir. I'm getting. I thought means there is a positive sequence
Nothing
current.
meaning.
No, sir.
Nothing meaning.
I thought any current is there in there.
Nothing current. See, simply this is one statement regularly you can observe in many problems. A certain element is offering this much percentage of reactance for positive sequence current. In the sense that is positive sequence reactance.
Okay, sir.
Okay. Rather than following this method, they have done something. That x into z base equals to x by z base equals to 0.15 they have taken. Then calculated x value multiplying with z base. Nothing.
Yes,
no need to do that much lengthy also.
Okay, sir.
Okay.
Okay.
Yeah, that's
Thank
it, in charge.
Yes, sir. Thank you.
Yeah. Swapnil.
Hello, sir.
Tell me, Swapnil.
Sir, actually, I have one question. I have sent on a Telegram.
Okay. What's the question you have?
Sir, it about fault. Previous year question, sir.
What is that? Can you read now?
50 hertz alternator is rated 500 MVA, 20 kV with XD is equal to 1 per unit and XD double dash is equal to 0.2 per unit. It supply purely resistive load of 400.
No option in the no correct answer in the options.
Okay, sir. And sir,
You will get
another one.
5.03 something.
Yes, sir. So
That
that's
you
why
don't
I'm
find it.
Yes.
But I have seen some student has asked me the same doubt. So
Okay,
somebody is teaching in YouTube. They have taken XD initially, then they have taken XD double dash during fault. They got some
Yes.
options are in the things given.
Yes.
Don't
sir.
manage the problem. It's a question given in Stevenson textbook.
Okay, sir.
Question copied from Stevenson's textbook.
Okay.
And
yes.
in the solution copy, he said
And
the answer is 5.03.
Okay, sir. Okay.
Okay.
And sir, one another question. In that question, sir, there is a way how to calculate circuit breaker rating, but in solution, I actually saw they did not calculate circuit breaker rating at circuit breaker. They calculated at another end.
Maybe you have only breaker, right? There is no other element. Only breaker
No,
you
sir.
might be having.
No, sir.
At the end of the line, you might be having a breaker. That's it.
Sir, there is a breaker, and after that there is some reactance, and after that there is just a they return load, and there I think there is load is not connected. But while calculating the circuit breaker rating, they calculated with considering that reactance also. They did not consider
Is it a 5
calculated
mark
at.
question asked in GATE exam?
Actually, sir, it is a 1991 year question.
Previous GATE question, 5 marks.
Yes. I think I don't know how much
That
mark.
one only.
Okay,
5
sir.
marks
Actually,
question.
I send on Telegram. Can you see, sir?
Can you resend again? There is
Yes.
number of requests here.
Okay.
What's your Telegram name?
Gate like this.
477.
Yes, sir. Sir,
It's okay.
this question.
A 100 MVA generator with 10% reactance.
Yes, sir. And here, sir, is the third question. MVA rating of circuit breaker C will be.
1 minute.
Yes.
MVA rating of C, if he is asking, you can take the fault at this nearby C only.
Yes, sir. But in solution, they have given that they taken the
This
fault.
15% whatever you have, above that breaker 15% what you have, that you no need to consider.
Okay, means they have, I think they give me wrong solution then.
It may be. You correct it. You correct it once and send me the solution.
Okay.
Have you
If, sir,
calculated X value first?
sir, I will send solution just a minute.
Okay.
Actually.
Hello, sir.
Tell me, Sajiram.
Sir, I send you that photos of that inductor everything, sir. WhatsApp.
WhatsApp you sent?
Yes, sir.
That's not inductive actually. That is for freedom.
Sir?
That's for freedom.
Freedom means what, sir?
Whenever you turn that switch, AB switch, whenever you are turning,
Okay, sir.
it will provide some loose.
Okay.
Don't tight it. Understood?
And this rod is connected to that.
Yes. Whenever you are turning that rod, if you don't connect that spring type of thing, if you simply keep a wire, then the wire may be stretched, right?
Yes, sir.
Then it may damage.
Yes, sir.
If you keep that spring type of thing, flexibly it can move.
Okay, sir.
That's physical reason.
Okay, sir.
Okay.
Hello, sir.
Yeah, tell me, Swapnil.
Yes, sir. I actually send solution on Telegram. So you can see.
You send this solution. Have you done your own solution? I'm asking about your solution.
Yes, sir. I actually did my solution. I get 1500 MVA.
MVA of how much is X value?
X value is 0.16 pu on the base 100 MVA. On
the base of 100 MVA, you got 0.16, huh?
Yes.
Okay, you tell me this number quickly. 0.16 plus 0.08. 1 minute.
0.24.
1 minute.
Yes.
0.16 plus 0.04. 0.2. 0.2 in pair with 0.1.
0.2
in pair with 0.1.
0.2 into 0.1 divided by 0.2 plus 0.1. 0.066.
Okay, 100 by that number.
Divide by
100 by that 0.0666.
Okay. 1500, sir.
That's your answer.
Okay, sir. Actually, same I got that. Okay. And sir, while calculating the circuit breaker rating at bus 1, also they did not consider this 15%.
No, they have connected some load actually.
But sir,
keep it at least as no load.
Yes, sir. They actually connected load, but
yes, they have to give some information regarding load. They have not given it.
Yes, sir. They did not give any information about it. And sir,
we can assume that load then.
Yes, sir. They just given there is a load, but they did not mention anything about load. Maybe there is something.
If you feel that as almost like infinite bus, for example.
Yes. Okay.
Then your breaker rating will be 100 by 0.0. Same answer we get again. Again, X value will change, right? You consider that load almost like an infinite bus.
Okay. Infinite
almost like an infinite bus if you consider.
Okay.
It's a big system if you take, for example.
If you want to consider.
At the time, X calculation will be deferred.
Yes, sir. Yes. Okay, sir. Got it, sir.
So of course, no information regarding load. That is one clarity what we can get.
Okay, sir.
Yeah.
And sir, on Telegram, sir, previously I just sent one question. It is actually based on transmission line fault.
Okay, tell me.
Just sir, before you can see.
Just before fault, there is no current flow, right? Operating under no load.
No, sir. Actually, this question is clear. I have another question which is sent previous this question in
Previous
Telegram.
question only I am saying you.
First question, sir. First question.
First
I will
question
just,
only.
okay.
Before the fault occurrence, we don't have any current flow in the line, right?
Before the fault occurrence. Okay.
And
So
just
there,
after the fault occurrence, also current will be zero because we have an inductor.
okay. Means,
Inductor will not
yeah.
accept sudden changes in the current.
Okay. Therefore, we take 0.
Hmm.
Okay. Thank you so much, sir.
Yeah. Fine.
Yes, cleared, sir. Thank you.
Yeah. Yogashri,
Sir,
tell me, Imtiaz.
sir, I sent one question. I did answer, but I'm not getting that perfect sequence.
That will discuss in JetBus. That will discuss in JetBus. Without having idea of JetBus, even though you do that problem, you can't get exact clarity. You don't get
No,
the
sir.
clarity.
At one bus they default. At one bus they are getting the voltage. That problem. How to do that problem, sir?
That's what I am saying you, Imtiaz. It will come in JetBus.
JetBus means next chapter.
Next chapter. Our system matrices will discuss. No.
Okay.
There we will discuss about that one.
Okay, sir.
Okay. Yogashri. Yogashri, tell me, Yogashri.
Sir, I'm asking 200.
200. Okay.
Sir, ఇక్కడ స్టార్టింగ్ మనం స్టేబుల్ రేట్ తర్వాత కర్వ్స్ మళ్ళీ స్టేబుల్ అయిపోయింది కదా సార్. మనం ఇక్కడ ముందు తీసుకుంటామా తర్వాత లాస్ట్ స్టేబుల్ అయ్యేది తీసుకుంటామా?
At this point only we may stop our analysis.
సరే మళ్ళీ రివర్స్ వస్తుందా సార్ కరెంట్ పాసింగ్ అంటే?
కరెంటా?
సరే ఇప్పుడు వేవ్ లో నుంచి వెళ్తుంది కదా సార్ డెల్టా డి బై dt. ఆ వేవ్ నుంచి ఇట్లా వెళ్తున్నప్పుడు మళ్ళీ స్వింగ్ కర్వ్ అన్నారు కదా సార్, మళ్ళీ రిటర్న్ వస్తుందా?
Yes, it will come. After getting the d delta by dt equals 0, it will return back, right?
స్టార్టింగ్ లో కూడా 0 ఉంది కదా సార్.
Before occurrence of disturbance, it is 0. Before the disturbance occurrence, it is 0. d delta by dt.
మళ్ళీ 0 అయినప్పుడు అది స్టేబుల్ అయిపోతుందా సార్ ఇక్కడ?
మళ్ళీ 0 అయితే we will say it is stable, but it is not final point. To know that final point, you should study some more. After reaching to this point, I am saying that d delta by dt was 0. Getting?
Okay, sir. Okay.
But this is not the final point where you stay, right?
Yes, sir. మళ్ళీ కిందకి వెళ్తుంది.
Yes. It will make some oscillation, and finally it will settle down to some other angle. If you want to know that, you should do some more things, some more analysis you have to do. But once after getting d delta by dt equals 0, you can confirm that system is stable. That's it?
Yes, sir.
Any other doubt you have, Yogashri?
No, sir.
Yeah, fine. So anybody having doubts, please raise your hands, else we can leave. Murali Krishna?
Sir, good evening, sir.
Tell me, Murali Krishna.
ఈ స్లైడ్ లో మామూలుగా మనం యాంగిల్ మినిమం అదే 30 degrees అది చెప్పారు కదా సార్, అందుకు అక్కడ 0 నుంచి స్టార్ట్ కావడంలో పైన వచ్చింది కదా సార్, అంతే కదా సార్?
ఇనిషియల్ ఆపరేటింగ్ యాంగిల్ కొంచెం ఉంటుంది కదా,
దాని నుంచి అదే స్టార్టింగ్ లో అవ్వలేదు. ఓకే సార్. సార్ ఇంకోటి సార్, ఏదైనా పాసిబుల్ అయితే శనివారం షెడ్యూల్ ఏమైనా చేంజ్ చేయండి సార్. 2 o'clock అంటే ఇబ్బంది అవుతుంది. అంటే ఎందుకంటే ఐ మీన్ వర్క్ చేసి వచ్చేటోళ్ళకి అది ఇబ్బంది అవుతుంది సార్.
Then we should go for morning session and evening session.
అదే సార్ ఈవినింగ్ అయితేనే బాగుంటుంది సార్. ఈవినింగ్
No,
5
no.
అయితే
Morning and evening.
Sir?
Morning, let us say 6 to 8 morning.
ఓకే సార్. కరెక్టే సార్. కానీ
Okay, sir.
మరి మిగతా
Morning
వాళ్ళ
better.
పరిస్థితి
Yeah, that's
మిగతా
right.
వాళ్ళకి కూడా ఓకే అవ్వాలి కదా సార్. అందుకు బెటర్ సండేనే షెడ్యూల్ సెట్ చేస్తే బాగుంటుంది సార్.
Sunday already we have 2 to 9, no?
ఎస్ సార్. ఎస్ సార్.
More than 7 hours, it may not be possible.
సార్ యాక్చువల్ అంటే శనివారం హాలిడే అన్నారు. కానీ హాలిడే
Tomorrow I am
లేకపోయినా
giving,
పర్లేదు
right?
కానీ అదే సార్ హాలిడే లేకపోయినా పర్లేదు కానీ అయితే షెడ్యూల్ 2 o'clock అంటే మరి కొంచెం వర్క్ ఉండే వాళ్ళకి ఇబ్బంది అవుతుంది సార్ అంతే.
It's 2 days. It's 2 days.
ఏమన్నా చూడండి పాసిబుల్ అయితే చూడండి.
Yeah. Okay.
సరే సార్. ఓకే సార్. థ్యాంక్ యూ.
Okay. Okay. Any other doubts? Can we leave today? Thank you.